We usually picture space as empty, black, quiet, and mostly nothing. But that picture breaks down close to home. The sun, Earth, and everything we see in the night sky from here are sitting inside something large, structured, and active. It's not a cloud, not a void, and not a solid object. It's a bubble, a galactic-scale bubble carved into the Milky Way itself. This isn't a metaphor. Astronomers call it the local bubble, and it's a real physical region of space, hundreds of light years across, where the normal mix of gas and dust has been swept aside. Inside it, the environment is hotter, thinner, and very different from the space beyond its edges. And it didn't form quietly. It was shaped by explosions. Multiple stellar deaths, spread out over millions of years, pushed outward and hollowed out a cavity in the galaxy. We just happen to be living inside it. What makes this more than a static structure is that it's still changing. The local bubble isn't frozen in time. It has a history, a measurable shape, and signs of motion. Parts of it are expanding. Its boundaries interact with surrounding gas, and its existence affects everything from nearby star formation to the kind of radiation that reaches Earth. The strange part isn't that bubbles like this exist. The strange part is how long it took us to realize we were inside one. A galactic bubble is not an empty hole in space, and it's not a solid shell either. It's a region of the interstellar medium where normal conditions have been dramatically altered. To understand what that means, you first have to understand what space inside a galaxy is usually like. Between stars, the Milky Way is filled with gas, dust, magnetic fields, and high-energy particles. This mixture is called the interstellar medium. It isn't uniform. Some regions are dense and cold, packed with molecular clouds where new stars form. Other regions are warmer, thinner, and more diffuse. But even in its thinnest state, the interstellar medium still contains matter. On average, there are a few atoms per cubic centimeter, along with dust grains and charged particles threaded by magnetic fields. A galactic bubble forms when that normal balance gets disrupted by energy on a massive scale. The most common source of that energy is dying stars. When massive stars end their lives in supernova explosions, they release enormous amounts of energy in a very short time. That energy heats nearby gas to millions of degrees and drives it outward at high speed. Stellar winds from massive stars, streams of charged particles flowing outward over millions of years, can do the same thing, though more gradually. When enough of these events happen close together in space and time, the surrounding gas gets pushed away faster than it can fall back in. The result is a cavity, a region where the gas density drops far below normal and the temperature rises sharply. That cavity is what astronomers call a bubble. The word bubble is useful, but it can be misleading if taken too literally. There is no soap-like surface. There is no clean boundary. Instead, there is a transition zone. Inside the bubble, gas is extremely thin and very hot, often millions of degrees. Outside the bubble, gas is cooler and denser. Between the two is a complex boundary where gas piles up, cools, fragments, and interacts with magnetic fields. That boundary is often where some of the most interesting physics happens. Galactic bubbles can range widely in size. Some are only a few dozen light-years across, created by a single supernova. Others span hundreds or even thousands of light-years and are shaped by multiple generations of stars. The largest ones are sometimes called superbubbles. These are formed when entire groups of massive stars, known as stellar associations, live and die in the same region. Each star adds energy to the same expanding cavity, reinforcing it over millions of years. The Milky Way is filled with these structures. They overlap, collide, and distort one another. From above the galaxy, if you could see the interstellar medium directly, it would look less like a smooth disk and more like a froth. Cavities, shells, filaments, and arcs would dominate the view. Bubbles are not rare features. They are one of the basic building blocks of the galaxy's structure. One important detail is that bubbles are defined not just by low density, but by temperature and pressure. Inside a typical galactic bubble, gas can reach temperatures of 1 to several million Kelvin. That sounds extreme, but because the gas is so thin, it doesn't behave the way hot gas does on Earth. You wouldn't feel heat in the usual sense. The particles are energetic, but there are so few of them that energy transfer is minimal. This hot, low-density gas emits mostly in X-rays, not visible light. That's one reason galactic bubbles went unnoticed for so long. Early astronomy relied heavily on optical telescopes, which are effectively blind to these structures. It wasn't until X-ray astronomy matured in the late 20th century that scientists began to see large-scale cavities in the interstellar medium. Another defining feature of a galactic bubble is motion. These regions are not static. When a bubble forms, it expands outward, pushing against surrounding gas. Over time, that expansion slows as energy dissipates and pressure equalizes. But even old bubbles can retain internal motion, turbulence, and temperature gradients for tens of millions of years. Magnetic fields play a major role here. The Milky Way's magnetic field is weak by everyday standards, but strong enough to shape the behavior of ionized gas. As a bubble expands, it stretches, compresses, and distorts magnetic field lines. Those distorted fields, in turn, affect how gas flows, how cosmic rays propagate, and how the bubble evolves. This feedback makes galactic bubbles far more complex than simple blast waves. Dust is another key piece. Interstellar dust grains are tiny, often smaller than a micron, but they carry a lot of influence. They absorb and scatter light, help molecules form, and respond differently to forces than gas does. Inside bubbles, dust is often destroyed or swept to the edges. That's why bubble interiors are relatively dust-free, while their boundaries can become dense, dusty shells. Those shells matter. When gas is pushed outward, it doesn't just disappear. It accumulates. In some cases, the compressed gas at the edge of a bubble can become dense enough to trigger new star formation. This means bubbles can both end stellar lives and help start new ones. A single generation of stars can reshape its environment in a way that influences the next generation. It's also important to separate galactic bubbles from other similar-sounding structures. They are not the same as planetary nebulae, which are shells of gas expelled by dying low-mass stars. They are not the same as supernova remnants, which are the immediate expanding debris from a single explosion. A galactic bubble is larger, longer-lived, and shaped by multiple energy sources interacting with the broader interstellar medium. Nor are galactic bubbles empty voids like cosmic voids between galaxies. Those are vast regions shaped by gravity on the largest scales of the universe. Galactic bubbles operate on much smaller scales and are driven by stellar physics, not cosmic expansion. Another subtle but important point is that bubbles are defined relative to their surroundings. A region is considered a bubble because it contrasts with nearby space. If the entire galaxy were uniformly hot and thin, bubbles wouldn't stand out. It's the patchwork nature of the interstellar medium that makes them meaningful structures. Because of this, identifying a bubble is not always straightforward. Astronomers rely on multiple kinds of data: X-ray emission to trace hot gas, absorption lines in stellar spectra to measure gas density, radio observations to map neutral hydrogen, and dust maps to see where material has been cleared or piled up. A true galactic bubble leaves signatures across many wavelengths. These observations often reveal that bubbles are irregular. They leak. They rupture. Hot gas can escape through weak points in the surrounding shell, venting into larger cavities or into the galactic halo. This process, sometimes called blowout, helps circulate energy and material throughout the galaxy. It's one of the ways galaxies regulate their internal environments. In that sense, galactic bubbles are part of a larger ecosystem. Stars form from dense gas, stars inject energy back into that gas, bubbles form, gas is redistributed, and new stars eventually emerge elsewhere. The galaxy is not a static backdrop. It's an active system constantly reshaped by these feedback loops. From a distance, this activity would be invisible in visible light. But in other wavelengths, especially X-rays and radio, bubbles stand out as some of the most prominent features of galactic structure. They tell a story about where stars lived, how they died, and how their energy reshaped the space around them. A galactic bubble, then, is best understood not as an object, but as a condition. It's a region where space has been heated, thinned, and rearranged by stellar energy. Its boundaries are fuzzy, its interior is dynamic, and its influence extends far beyond its apparent size. Once you grasp that definition, the next realization becomes unavoidable. If bubbles are common, and if they can span hundreds of light years, then the chances of stars and planets existing inside one are not small. In fact, given the way galaxies work, it would almost be surprising if we weren't inside one at all. The local bubble is the specific galactic bubble we live in. It's not centered on the sun, it wasn't made for us, and it's not unique in the Milky Way. But it is the environment that surrounds the solar system right now, and it defines the physical conditions of interstellar space in our neighborhood. The first thing to be clear about is scale. The local bubble is enormous compared to anything in the solar system. Estimates put its diameter at roughly 600 to 1,000 light-years, depending on direction. That means light takes centuries to cross it. The Sun sits well inside this cavity, not near the center but comfortably away from the densest surrounding walls. Earth, every planet, and the entire heliosphere are embedded in this structure. Despite its size, the local bubble is not something you can see by looking up at the night sky. Stars inside and beyond it still shine normally. The bubble is made of gas that is far too thin to glow visibly. Its presence has to be inferred indirectly through careful measurements of what lies between stars rather than the stars themselves. Inside the local bubble, the interstellar medium is extremely sparse. Typical densities are around 0.005 atoms per cubic centimeter, sometimes even lower. For comparison, outside the bubble, densities are often closer to 0.5 or 1 atom per cubic centimeter, and in dense clouds they can be thousands or millions of times higher. This means the local bubble is not just slightly emptier than average space, it is radically depleted. At the same time, the gas inside the bubble is hot. Temperatures are measured in the range of 1 to several million Kelvin. This combination of low density and high temperature tells astronomers immediately that something energetic must have happened here. Cold, dense gas does not spontaneously become hot and rarefied. Energy had to be injected, and in large amounts. The local bubble was not discovered all at once. Its existence emerged gradually as different observations started to line up. In the mid-20th century, astronomers noticed that nearby stars showed unusually low levels of interstellar absorption. Starlight traveling through space is partially absorbed by gas and dust, leaving characteristic fingerprints in spectra. For stars within a few hundred light-years, those fingerprints were much weaker than expected. That suggested that the space around the Sun contained very little intervening material. At first, this was just described as a local cavity or local hole in the interstellar medium. The idea of a coherent bubble came later when X-ray observations entered the picture. When X-ray telescopes began mapping the sky, astronomers detected a diffuse background glow of soft X-rays coming from all directions. This emission couldn't be explained by distant galaxies alone. It was too uniform and too local. The most consistent explanation was hot gas surrounding the solar system, emitting X-rays because of its high temperature. When these two lines of evidence were combined, low absorption toward nearby stars and diffuse X-ray emission, the picture of a hot, low-density cavity around the Sun became difficult to avoid. That cavity is what we now call the local bubble. The local bubble is not empty even by interstellar standards. Within it are small, cooler clouds of gas drifting through the hot plasma. The solar system is currently passing through one of these, known as the local interstellar cloud, or sometimes the local fluff. This cloud is only a few tens of light-years across and has a higher density than the surrounding bubble interior, though still extremely thin by everyday standards. These embedded clouds matter because they interact directly with the heliosphere, the bubble blown by the solar wind. The pressure, density, and magnetic field of the surrounding interstellar medium influence how far the heliosphere extends and how it shields the solar system from cosmic radiation. The fact that we are inside a hot bubble with small, cooler clouds embedded in it is a key part of that interaction. The shape of the local bubble is highly irregular. It is not spherical and it is not symmetric around the Sun. In some directions, its boundary lies a few hundred light-years away. In others, it stretches farther, possibly connecting to neighboring cavities. Astronomers often describe it as more of a chimney or network of tunnels than a simple hollow ball. One prominent feature is that the local bubble appears to open upward and downward, perpendicular to the plane of the Milky Way. These openings allow hot gas to flow toward the galactic halo. This vertical structure makes sense given how supernova-driven bubbles behave in disk galaxies. The disk is relatively thin, so it's easier for hot gas to escape vertically than to push through dense material along the plane. The walls of the local bubble are where most of the displaced material ended up. These walls are regions of denser gas and dust, often traced by neutral hydrogen emission and dust extinction maps. Many nearby star-forming regions lie along these boundaries, suggesting that the compression caused by the bubble played a role in shaping them. Some of the most familiar nearby molecular clouds, including those associated with well-known constellations, sit right at the edges of the local bubble. Their locations are not random. They are part of the larger structure formed when expanding hot gas swept material outward and piled it up. The Sun's position inside the local bubble is not permanent. The solar system moves through the galaxy at about 220 kilometers per second as it orbits the galactic center. On top of that, it has its own motion relative to nearby stars and gas. Over millions of years, this motion carries the Sun through different interstellar environments. Based on current trajectories, the Sun likely entered the local bubble several million years ago. Before that, it would have been moving through denser interstellar material. In the future, it will eventually leave the bubble and enter a different region of the interstellar medium. These transitions happen on timescales far longer than human history, but they are short in galactic terms. The local bubble is also layered in time. It is not the result of a single event. Evidence points to multiple supernova explosions occurring in roughly the same region over a span of millions of years. Each explosion added energy, reheated gas, and pushed the cavity outward or reshaped it. Clues to this history come from several sources. One is the distribution of nearby stellar groups. Certain moving groups and stellar associations near the Sun contain stars whose ages and past positions line up with the energy required to create the bubble. By tracing their motions backward, astronomers can reconstruct where those stars were when they exploded. Another line of evidence comes from Earth itself. Layers of deep-sea sediments contain traces of radioactive isotopes, such as iron-60, that are produced almost exclusively in supernova. These isotopes have been dated to a few million years ago, suggesting that one or more supernova occurred relatively close to the solar system around that time. While these events did not necessarily create the entire local bubble, they are consistent with the idea that we live in an active, supernova-shaped environment. Inside the local bubble, pressure is dominated by thermal energy rather than particle collisions. The hot gas exerts pressure outward, helping maintain the cavity against collapse. Over time, as the gas cools and energy dissipates, that pressure decreases. But because the bubble is so large and the surrounding medium so structured, this process takes tens of millions of years. The local bubble does not exist in isolation. It is part of a larger complex of cavities and shells in the local region of the Milky Way. Neighboring bubbles include structures associated with nearby star-forming regions and older stellar associations. In some directions, the boundaries between these bubbles are fuzzy or overlapping, making it difficult to say where one ends and another begins. This interconnectedness complicates mapping efforts. Astronomers build three-dimensional maps of the local interstellar medium by measuring absorption toward thousands of stars at known distances. By combining these measurements, they can reconstruct where gas and dust are sparse and where they are concentrated. These maps reveal a tangled network of cavities, with the local bubble being just one prominent node. And from our perspective inside it, the local bubble influences almost every astronomical observation that involves nearby space. When we observe distant objects, the light first passes through this hot, thin region before encountering denser material farther out. Understanding the properties of the local bubble is therefore essential for interpreting data correctly. The local bubble also sets boundary conditions for models of the heliosphere. The size and shape of the heliosphere depend on the external pressure exerted by interstellar gas and magnetic fields. A denser surrounding medium would compress it more tightly. A thinner one allows it to expand farther. The current size of the heliosphere reflects the fact that we are inside a low-density bubble. Another subtle influence involves cosmic rays. These high-energy particles travel through the galaxy and are affected by magnetic fields and gas density. The local bubble's interior conditions can alter how cosmic rays propagate near the solar system, affecting the spectrum of particles that reach Earth. Despite decades of study, the local bubble is still being actively researched. Improved distance measurements from stellar surveys have sharpened our view of its boundaries. Better X-ray data have refined estimates of its temperature and internal structure. Each new dataset adds detail to what was once a vague idea of a local cavity. What makes the local bubble especially interesting is not just that it exists, but that it places the solar system in a specific galactic context. We are not floating in average space. We are embedded in the aftermath of multiple stellar deaths inside a region that has been heated, evacuated, and reshaped by events far more energetic than anything the sun will ever produce. This environment is not hostile in the everyday sense. The distances are too vast and the densities too low for direct danger, but it is dynamic, structured, and historically violent. The space between the stars around us carries the imprint of explosions that happened long before Earth existed, yet still define the conditions of space today. Understanding our place inside the local bubble means recognizing that even the emptiness around us has a history. It has been carved, pushed, and altered. The sun did not form in this bubble, but it now travels through it, carrying its planets along for the ride through a region of space shaped by forces on a galactic scale. Galactic bubbles don't appear all at once. They form through a sequence of events that unfold over millions of years, driven by how stars live, interact with their surroundings, and eventually die. To understand bubble formation in the Milky Way, you have to look at how energy moves from stars into the interstellar medium and how that medium responds. The process usually begins in regions where stars form in groups. Massive stars almost never form alone. They are born in clusters or loose associations inside dense molecular clouds. These clouds are cold, dusty, and heavy, and they sit embedded in the galactic disk. When star formation ignites, it doesn't just produce light. It produces motion, heat, and pressure that immediately start altering the surrounding environment. Even before the first star dies, bubble formation can already be underway. Massive stars emit intense ultraviolet radiation that strips electrons from nearby gas, turning it into ionized plasma. This creates expanding regions of ionized hydrogen that push outward from the star. At the same time, these stars generate powerful stellar winds, continuous outflows of charged particles traveling at hundreds or even thousands of kilometers per second. Those winds slam into surrounding gas and dust, transferring momentum and energy. Over time, they carve out low-density cavities around the stars. On their own, stellar winds can create modest bubbles, tens of light-years across. But in a cluster with many massive stars, their winds overlap and reinforce each other, creating a larger shared cavity. The real transformation happens when the first supernova goes off. A supernova releases an enormous amount of energy in a very short time, roughly equivalent to what the sun will emit over its entire lifetime. When the explosion occurs, a shock wave races outward, heating and compressing everything it encounters. In a dense molecular cloud, this shock can quickly lose energy and stall. But if it occurs inside a pre-existing cavity created by stellar winds, the shock can travel much farther. This is where bubble growth accelerates. Each supernova dumps fresh energy into an already rarefied region, reheating the gas and pushing the boundary outward. If multiple supernovae occur within a few million years and within a few tens of light-years of each other, as is common in stellar associations, their effects stack. Instead of a single expanding shell that fades away, you get a sustained expansion driven by repeated energy injections. The interior stays hot because it keeps getting reheated. The surrounding gas keeps getting pushed outward faster than it can flow back in. This is how large galactic bubbles and superbubbles are born. The Milky Way's disk plays an important role in shaping this process. The disk is thin compared to its diameter, with most gas concentrated near the galactic plane. As a bubble expands, it encounters different resistance depending on direction. Expansion along the plane runs into dense gas and slows down. Expansion perpendicular to the plane meets less resistance and accelerates. This imbalance often leads to vertical elongation. Many bubbles stretch upward and downward, forming chimney-like structures that channel hot gas away from the disk. In extreme cases, these chimneys break through entirely, allowing gas to vent into the galactic halo. This vertical escape is a key part of how energy from supernova gets redistributed on galactic scales. The physics inside an expanding bubble is complex. Right after a supernova, the interior gas is extremely hot and turbulent. Shock fronts ripple through it, collide and reflect off denser regions. Over time, the gas begins to cool by emitting radiation, mostly in X-rays, but because the density is so low, this cooling is inefficient. Hot gas inside a bubble can remain at million-degree temperatures for tens of millions of years. As the bubble expands, it sweeps up surrounding material. This material doesn't vanish. It piles up at the edges, forming a shell. The shell grows denser as more gas and dust are added. Gravity, turbulence, and magnetic fields all influence how that shell evolves. It can fragment, wrinkle, and develop clumps. In some regions, these clumps become gravitationally unstable. When that happens, new stars can begin forming in the compressed gas. This means that bubble formation can directly trigger star formation at its edges, even as it clears out material from its interior. The same event that destroys a star-forming cloud in one place can help create stars somewhere else. Magnetic fields complicate this picture further. The Milky Way's magnetic field threads through the interstellar medium and resists compression in certain directions. As a bubble expands, it drags magnetic field lines along, stretching them and piling them up at the boundary. This can stiffen the shell in some directions and allow easier expansion in others. Because of this, bubbles are rarely round. Their shapes reflect the structure of the surrounding gas, the orientation of magnetic fields, and the timing and placement of energy injections. Two bubbles formed by similar numbers of supernovae can look completely different if their environments differ. Another factor is timing. If supernovae are spaced too far apart in time, the bubble may partially collapse or cool between events. In that case, each explosion acts more like an isolated event, and the cavity never grows very large. To form a large, coherent bubble, energy input has to be relatively continuous on million-year timescales. This requirement is naturally met in stellar associations, where massive stars have similar ages. The most massive stars explode first, followed by slightly less massive ones. This staggered sequence ensures that the region keeps receiving energy over an extended period. The result is a long-lived hot cavity rather than a brief flash of expansion. Galactic rotation also plays a role. As gas orbits the center of the Milky Way, different parts of an expanding bubble move at slightly different speeds. Over millions of years, this shear can distort the bubble's shape, stretching it into elongated or twisted forms. What began as a roughly spherical cavity can end up looking lopsided or torn. The surrounding interstellar medium is not smooth either. Dense clouds act like obstacles. When an expanding bubble runs into one, the expansion can stall locally while continuing elsewhere. This creates dents and protrusions in the bubble's boundary. In extreme cases, the bubble can wrap around dense clouds, leaving them embedded like islands inside a sea of hot gas. Some of these clouds survive inside bubbles for surprisingly long times. Shielded by their density and magnetic fields, they can drift through the hot interior without being completely destroyed. Over time, they may evaporate, fragment, or collapse to form stars, depending on conditions. As bubbles grow and interact, they often collide with neighboring bubbles. When two expanding cavities meet, their shells can merge or fragment. The hot interiors can mix, forming larger, more complex structures. Much of the Milky Way's interstellar medium has been processed multiple times by overlapping bubbles from different generations of stars. This recycling is continuous. Gas pushed into a shell today may form stars tomorrow. Those stars may later explode and carve new bubbles that reshape the same region again. There is no final, stable configuration. Bubble formation is part of an ongoing cycle of energy injection and redistribution. From an observational standpoint, astronomers identify forming bubbles by looking for expanding shells of gas, velocity patterns that indicate outward motion, and temperature contrasts between interiors and surroundings. Young bubbles show strong shock signatures and rapidly expanding shells. Older ones show weaker expansion but retain hot interiors and complex boundaries. The Milky Way contains thousands of such structures at various stages of evolution. Some are actively growing. Others are fading as their interiors cool and mix back into the surrounding medium. A few have grown so large that they dominate entire regions of the galactic disk. Importantly, bubbles do not require extreme conditions unique to our galaxy. The same processes operate in other spiral galaxies, dwarf galaxies, and even starburst galaxies, though the scale and intensity can differ. What changes is the density of gas, the rate of star formation, and the frequency of supernovae. In the Milky Way, bubble formation is a natural consequence of normal star formation. As long as massive stars are born in groups, and they are, bubbles will continue to form. They are not rare anomalies. They are the expected outcome of how energy flows from stars into their surroundings. Seen this way, a galactic bubble is not an accident or a curiosity. It is the visible footprint of stellar life cycles written into the structure of the galaxy. Every large bubble marks a place where stars once lived together, shaped their environment, and left behind a cavity that can persist long after the stars themselves are gone. The Milky Way's interstellar medium is therefore not a quiet backdrop, but a record of repeated, overlapping bubble formation. Each cavity tells part of the story of how the galaxy renews itself, one generation of stars at a time. Galactic bubbles do not inflate themselves. They are powered by energy sources capable of overpowering the normal pressure of the interstellar medium and keeping large regions of space hot and rarefied for millions of years. In the Milky Way, two mechanisms dominate this role: stellar winds from massive stars and supernova explosions. Together, they act as the engines that carve, heat, and maintain galactic bubbles. The process starts long before a star explodes. Massive stars, those with more than about 8 times the mass of the Sun, live fast and violently. Even while they are still burning nuclear fuel in their cores, they pour energy into their surroundings. One of the main ways they do this is through stellar winds. A stellar wind is a continuous outflow of particles, mostly protons, electrons, and heavier ions, driven off a star's surface by radiation pressure and magnetic fields. For low-mass stars like the Sun, these winds are relatively gentle. For massive stars, they are extreme. Wind speeds can reach thousands of kilometers per second, and the total mass lost over the star's lifetime can amount to several times the mass of the Sun. These winds carry momentum and energy outward. When they collide with surrounding interstellar gas, they create shock fronts. Gas behind the shock is heated and pushed outward, while gas ahead of it gets compressed. Over time, this interaction hollows out a cavity around the star or star cluster, lowering the density of gas in the interior and raising its temperature. In isolation, a single massive star's wind might carve out a modest bubble, but massive stars rarely exist alone. They form in groups, often dozens or hundreds at a time within the same region. When their winds overlap, the combined effect is far more powerful. The winds merge into a collective outflow that inflates a shared cavity, sometimes called a wind-blown bubble. This wind-driven phase sets the stage for what comes next. By the time the first supernova occurs, the surrounding region has often already been partially cleared of dense gas. That clearing is crucial. Supernovae exploding into dense material lose energy quickly, but supernovae exploding into a low-density cavity can drive much larger expansions. When a massive star reaches the end of its life, its core collapses and triggers a supernova explosion. In a fraction of a second, gravitational energy is converted into an outward blast that ejects the star's outer layers at speeds of tens of thousands of kilometers per second. The initial shock wave is extraordinarily energetic, but it doesn't remain that way for long. As the shock expands, it sweeps up surrounding material, slowing down and heating the gas it encounters. In the earlier stage, the expansion is almost free, dominated by the momentum of the ejected material. Soon after, it enters a phase where energy conservation becomes more important, and the shock's behavior is governed by how efficiently it transfers energy to the interstellar medium. If the supernova occurs inside a cavity carved by stellar winds, the shock travels farther before slowing significantly. The hot interior gas absorbs the energy and spreads it throughout the bubble. This reheats the cavity and drives its expansion outward, reinforcing the structure already formed by winds. What makes supernovae especially important is not just their energy, but their timing. In a stellar association, massive stars don't all explode at once. They die in sequence over several million years. Each explosion adds a fresh pulse of energy to the same region. This repeated input keeps the interior hot and pressurized, preventing the bubble from collapsing. The cumulative effect of multiple supernovae is much greater than the sum of individual explosions occurring in isolation. Energy that would otherwise radiate away gets trapped inside the low-density cavity, maintaining high temperatures and driving large-scale expansion. This is how superbubbles form, structures far larger than any single supernova remnant. The energy budget involved is immense. A single supernova releases on the order of 10 to the power of 51 ergs of energy. When dozens of such events occur in one region, the total energy rivals that of some of the largest processes shaping the galactic disk. Even with losses to radiation and turbulence, enough energy remains to excavate cavities hundreds of light-years across. Stellar winds and supernovae also differ in how they interact with magnetic fields. Winds tend to gradually stretch and bend magnetic field lines as they push outward. Supernova shocks, by contrast, can strongly compress and amplify magnetic fields at their fronts. These amplified fields influence how particles move, how shocks propagate, and how energy is distributed inside the bubble. Another important difference lies in chemical enrichment. Stellar winds, especially from evolved massive stars, carry heavy elements forged in stellar interiors. Supernovae add even more, ejecting newly synthesized elements like oxygen, silicon, and iron into the surrounding medium. Inside a bubble, these elements mix into the hot gas and eventually become part of the material that forms future stars and planets. This means galactic bubbles are not just empty cavities, they are chemically active regions where enriched material is stored and transported. Over time, as bubbles cool and mix with their surroundings, they help distribute heavy elements throughout the galaxy. The balance between winds and supernovae can vary depending on the stellar population. In very young regions dominated by the most massive stars, winds may dominate early shaping. As those stars begin to explode, supernovae take over as the primary drivers of expansion. In older associations, winds fade as massive stars die, but supernovae continue from slightly less massive stars. Environmental conditions also matter. In regions with higher ambient gas density, more energy is required to achieve the same level of expansion. In lower density environments, even a modest number of supernovae can create large bubbles. This is why bubbles in the outer parts of the galaxy can sometimes grow larger than those in denser inner regions. Not all the energy from winds and supernovae goes into expansion. A significant fraction is lost through radiation, turbulence, and the acceleration of cosmic rays. Supernova shocks are particularly efficient at accelerating charged particles to near-light speeds, seeding the galaxy with cosmic rays that carry energy far from their sources. These cosmic rays can escape the bubble entirely, influencing regions far away. In this way, the impact of a supernova extends beyond the visible cavity it helps create. Energy injected in one place can affect the galactic environment on much larger scales. Over time, as supernovae stop occurring in a given region, the engine winds down. Without fresh energy input, the interior gas begins to cool and lose pressure. Expansion slows. The surrounding interstellar medium starts to push back. Eventually, the bubble may fragment, collapse partially, or merge with neighboring structures. But even in this fading phase, the imprint of stellar winds and supernovae remains. The redistributed gas, distorted magnetic fields, and altered chemical composition persist long after the explosions themselves are over. In the Milky Way, this cycle repeats constantly. New stellar associations form. Massive stars light up and blow winds. Supernovae erupt, bubbles expand, and the interstellar medium is reshaped again. Stellar winds and supernovae are not rare events interrupting an otherwise calm galaxy. They are fundamental processes that drive its evolution. Without them, the Milky Way would look very different. Gas would remain more evenly distributed. Star formation would proceed differently. Heavy elements would be less well mixed. The large cavities and shells that define much of the galaxy's structure would simply not exist. In that sense, stellar winds and supernovae are the engines not just of galactic bubbles, but of the dynamic, ever-changing environment between the stars. Mapping a structure you're inside is much harder than mapping something you can view from the outside. That challenge defines nearly everything astronomers have had to deal with when trying to chart the local bubble. We don't see its edges directly. We don't see a shell in the sky. Instead, we have to reconstruct the bubble's shape by measuring how space behaves in different directions and at different distances from the Sun. The first tool for this job is starlight. As light travels from a star to Earth, it passes through interstellar gas and dust. Along the way, specific wavelengths get absorbed by atoms and molecules, leaving dark lines in the star's spectrum. The strength of those absorption lines tells astronomers how much material lies between us and the star. If a nearby star shows very weak absorption, that suggests the space between us and that star is relatively empty. If a more distant star in the same direction shows much stronger absorption, that implies the boundary of a denser region lies somewhere between the two. By repeating this process for many stars at known distances, astronomers can begin to locate where gas density increases sharply, essentially tracing the walls of the bubble. This method only works because stellar distances are known with high precision. For a long time, distance measurements were the limiting factor. Astronomers could detect absorption, but they didn't always know exactly how far away the absorbing material was. That changed dramatically with modern astrometric surveys, which provided accurate distances for millions of stars in the solar neighborhood. With precise distances in hand, absorption measurements could be converted into three-dimensional maps. Instead of vague suggestions of a cavity, astronomers began to see a detailed structure emerge, a region of very low density around the Sun, surrounded by denser gas arranged in an irregular shell. Dust mapping provides another key perspective. Interstellar dust absorbs and scatters visible light, making distant stars appear dimmer and redder than they otherwise would. By comparing the observed brightness and color of stars to what is expected based on their intrinsic properties, astronomers can estimate how much dust lies along the line of sight. When this is done for large numbers of stars across the sky, patterns appear. Nearby stars show little reddening, consistent with a dust-poor environment. Beyond a certain distance, reddening increases sharply in many directions. Those distances line up with the same boundaries inferred from gas absorption, reinforcing the picture of a surrounding shell. Dust maps are particularly useful because they can be constructed using broadband photometry, not just high-resolution spectroscopy. This allows astronomers to include far more stars in their analyses, improving spatial coverage and resolution. X-ray observations add a different layer of information. The hot gas inside the local bubble emits soft X-rays as it cools. Early all-sky X-ray surveys revealed a diffuse background glow that was strongest at low energies. Initially, there was debate about whether this glow came from distant sources or from local hot gas. By comparing X-ray intensity with absorption measurements, astronomers could test these ideas. In directions where interstellar absorption was low, X-ray emission was strong. Where absorption was high, X-rays were weaker. This anti-correlation strongly suggested that much of the soft X-ray background originated within the local bubble. X-ray data help constrain the temperature and pressure of the bubble's interior. Combined with density estimates from absorption, they allow astronomers to estimate how much energy is stored in the hot gas and how that energy is distributed. Radio observations are also essential, especially those targeting neutral hydrogen. Hydrogen emits radio waves at a characteristic wavelength of 21 centimeters, allowing astronomers to map its distribution and motion throughout the galaxy. In regions corresponding to the local bubble, neutral hydrogen emission is weak or absent, consistent with a low-density cavity. At the edges of the bubble, neutral hydrogen emission increases, tracing the denser shell. Velocity measurements of this gas can reveal whether it is moving outward, inward, or rotating with the galaxy. These motions help determine whether parts of the bubble are still expanding or have reached a more stable state. Combining these different datasets, optical absorption, dust reddening, X-rays, and radio emission, is not straightforward. Each probe responds to different components of the interstellar medium and has its own biases and limitations. Gas can be hot or cold, ionized or neutral. Dust can be clumpy. X-rays can be absorbed or scattered. To make sense of it all, astronomers use statistical reconstruction techniques. They divide the local region of space into small volume elements and estimate the density of gas and dust in each one based on all available observations. The result is a three-dimensional model of the local interstellar medium. These models show that the local bubble is highly irregular. Its boundaries twist and fold. In some directions, the bubble wall is sharp and close. In others, the cavity extends much farther, blending into neighboring low-density regions. There is no single radius that defines its size. One striking result of modern mapping is how asymmetric the bubble is. The Sun is not centered. In some directions, we are only a few hundred light-years from dense gas. In others, the low-density region extends nearly twice that distance. This asymmetry reflects the uneven distribution of supernovae that created the bubble and the non-uniform structure of the surrounding interstellar medium. Another important feature revealed by mapping is connectivity. The local bubble is not an isolated void. It connects to other cavities through narrow channels and openings. Some of these connections extend toward known star-forming regions, suggesting a shared history or interacting expansions. Vertical extensions are especially prominent. Maps show that the local bubble opens toward higher and lower galactic latitudes, connecting to larger low-density regions above and below the Milky Way's disk. These openings are consistent with the idea that hot gas has vented upward and downward over time. Mapping also reveals smaller structures embedded within the bubble. Local clouds of cooler gas appear as density enhancements inside the larger cavity. These clouds show up clearly in absorption data, even though they occupy only a small fraction of the bubble's volume. Because these clouds are small and irregular, they complicate the picture. A single line of sight may pass through hot, empty space for hundreds of light years, then encounter a dense cloud only a few light years thick. Without many sight lines, these features would be easy to miss. Time adds another layer of complexity. The maps we construct represent the present-day distribution of gas and dust, but the bubble itself is the product of past events. To understand how it formed, astronomers combine spatial maps with stellar motion data, tracing where nearby stars and associations were millions of years ago. By rewinding their orbits through the galaxy, it's possible to estimate where supernova progenitors were located when they exploded. These reconstructed positions often align with the center or edges of the local bubble, lending support to formation models based on multiple supernovae. As mapping techniques improve, the resolution of these models continues to increase. What once looked like a simple cavity now appears as a complex layered structure shaped by many overlapping processes. Fine-scale features emerge, such as thin filaments of gas, density gradients, and subtle asymmetries tied to magnetic fields. Despite all this progress, mapping the local bubble remains an ongoing effort. There are still directions with sparse data, especially toward the galactic plane, where dust obscuration is strongest. Hot gas is difficult to measure directly, and X-ray observations are affected by foreground contamination from the solar system itself. Even so, the overall picture is now clear enough to be robust. The Sun sits inside a large, hot, low-density cavity with irregular boundaries, embedded clouds, and connections to neighboring structures. This is not an inference from a single dataset, but a conclusion supported by multiple independent lines of evidence. What makes this mapping effort remarkable is that it turns the usual astronomical perspective inside out. Instead of observing distant objects through empty space, astronomers have had to treat the space around us as the object of study. Every spectrum, every distance measurement, every subtle dimming of starlight becomes a clue to the shape of the environment we inhabit. The local bubble is not drawn on the sky as a bright feature. It emerges only when enough data are combined, carefully and patiently, into a coherent three-dimensional picture. That picture continues to sharpen, revealing not just where the bubble is, but how intricately structured the space around us really is. Asking how big the local bubble is sounds simple, but the answer depends on direction, definition, and what you choose to measure. There is no single radius, no clean edge, and no uniform boundary. The local bubble is an irregular cavity with a size that changes depending on where you look and what tracer you use. Early estimates treated the bubble as roughly spherical, mainly because data were sparse and uneven. Based on absorption toward nearby stars, astronomers initially suggested a diameter of a few hundred light years. As more observations came in, especially with better distance measurements, that estimate expanded. Today, most models place the local bubble's extent between about 300 and 500 light years from the Sun in many directions, giving it a total diameter of roughly 600 to 1,000 light years. But those numbers hide a lot of complexity. In some directions, dense gas appears much closer. In others, the low-density region stretches farther, sometimes merging into neighboring cavities. The key reason for this variability is that the local bubble is not a neatly carved hole. It is the result of multiple supernovae expanding into a highly uneven interstellar medium. Where surrounding gas was dense, expansion slowed and the boundary formed closer in. Where gas was sparse, expansion continued farther. Astronomers determine the bubble's size primarily by locating where interstellar density increases sharply. This can be done using gas absorption lines, dust extinction, or radio emission from neutral hydrogen. Each method traces a slightly different component of the interstellar medium, and they don't always agree perfectly on where the boundary lies. Gas absorption measurements often show a clear jump in column density at distances of a few hundred light years. Dust maps show a similar pattern, little reddening nearby, then a rapid increase at certain distances. In many directions, these transitions occur around 300 to 400 light years, marking a likely bubble wall. However, there are directions where this transition is much more gradual or occurs much farther out. These are often directions where the local bubble connects to other low-density regions. Instead of hitting a dense wall, a line of sight may pass through a chain of cavities with no obvious boundary. Vertical size is another important dimension. Perpendicular to the galactic plane, the local bubble appears to extend farther than it does within the plane. In these directions, estimates suggest the cavity reaches several hundred light-years above and below the disk, possibly connecting to larger structures in the galactic halo. This vertical elongation is consistent with how bubbles expand in disk galaxies. The gas density drops rapidly away from the plane, offering less resistance to expansion. As a result, the bubble grows taller than it is wide, creating a chimney-like shape. The Sun's position within this structure also affects how size is perceived. We are not at the center. In some directions, the bubble wall is relatively close. In others, it is much farther away. If the Sun were closer to one side, the bubble might appear smaller overall, even if its total volume were the same. Another complication is that the local bubble's boundary is not a thin surface. It is a region of transition that can span tens of light years. Gas density, temperature, and ionization change gradually rather than abruptly. Depending on where you draw the line between inside and outside, the measured size can shift. Time also matters. The local bubble has evolved over millions of years, and its size has changed as it expanded, slowed, and interacted with surrounding structures. The size we measure today is a snapshot, not a permanent value. To estimate volume, astronomers often approximate the bubble as an irregular ellipsoid or a network of connected cavities. Even with these simplifications, the total volume is enormous. The local bubble contains millions of cubic light-years of space, where gas density is far below the galactic average. Despite this, the total mass of gas inside the bubble is quite small. Because the density is so low, the entire interior may contain less mass than a single dense molecular cloud. Size, in this context, does not translate to weight or substance. Comparisons help make the scale more concrete. The nearest star system beyond the Sun, Alpha Centauri, lies about 4.3 light-years away. That means there is room for dozens of such distances before even reaching the inner regions of the bubble wall. Most of the stars visible to the naked eye are still well inside the local bubble. Beyond that, some familiar star-forming regions lie right at or just beyond the bubble's edge. Their distances line up closely with where density increases, reinforcing the idea that they sit on the bubble's boundary. These regions help anchor size estimates to recognizable landmarks in the sky. Another way to think about size is through travel time. At the Sun's current speed relative to the local interstellar medium, it would take tens of millions of years to cross the bubble from one side to the other. Even at galactic speeds, this is not a small structure. Different research groups sometimes quote slightly different size ranges because they emphasize different datasets or definitions. Some focus on the hottest X-ray emitting region. Others focus on where neutral gas reappears. Still others use dust as the defining boundary. All are valid, but they describe slightly different aspects of the same structure. What unites these approaches is agreement on the overall scale. The local bubble is not a minor cavity. It is a dominant feature of the local interstellar environment, extending hundreds of light-years in most directions and shaping a large fraction of the space around the Sun. It's also important to note that local in this context is misleading. On human scales, the bubble is unimaginably vast. It is only local in the sense that it surrounds our immediate galactic neighborhood, not because it is small. As mapping improves, estimates of the bubble's size continue to be refined. Boundaries are traced more precisely. Substructures are identified. Connections to neighboring cavities become clearer, but these refinements are just the details, not the big picture. The local bubble is a large, irregular cavity, roughly 1,000 light-years across at its widest, with the Sun located well inside it. Any attempt to describe it with a single number will always be an oversimplification. Its true size is better understood as a range, shaped by direction, environment, and history. And that complexity is exactly what makes it a useful probe of how energetic events have sculpted the space around us. If the local bubble were a simple blast expanding into empty space, it might look roughly spherical. That's often how explosions behave in textbooks, energy released at a point, spreading evenly in all directions. But the Milky Way is not empty uniform space, and the local bubble is anything but spherical. When astronomers map the bubble's boundaries in 3 dimensions, the shape that emerges is irregular, distorted, and lopsided. It has bulges, narrow extensions, flattened regions, and apparent openings. In some directions, it looks like a rounded cavity. In others, it looks like a stretched tunnel or a broken shell. The most basic reason for this odd shape is that the interstellar medium is not uniform. Gas density in the Milky Way varies by orders of magnitude from one region to another. When the bubble expanded, it did not encounter the same resistance everywhere. Where surrounding gas was dense, expansion slowed or stalled. Where gas was thin, expansion continued farther and faster. This uneven resistance alone is enough to destroy spherical symmetry, but it is only part of the story. The local bubble formed from multiple supernovae, not a single explosion. Those supernovae did not all occur at the same position. Their progenitor stars were spread out over tens of light years and exploded at different times. Each explosion injected energy from a slightly different location, pushing the bubble in new directions or reinforcing expansion on one side more than another. As a result, the center of energy input shifted over time. The bubble's shape records this history. Bulges and asymmetries correspond to where energy input was strongest or most sustained. Regions that received fewer explosions or encountered dense clouds show less expansion. Magnetic fields further complicate the shape. The Milky Way's magnetic field threads through the interstellar medium and resists compression perpendicular to its field lines. As the bubble expanded, it stretched and piled up magnetic fields along certain directions. This made expansion easier in some orientations and harder in others. Over millions of years, this magnetic shaping can significantly distort the bubble. Instead of expanding evenly, the hot gas preferentially flows along paths of least magnetic resistance, creating elongated features and flattened surfaces. Galactic rotation adds another layer of distortion. The Milky Way rotates differentially, meaning that gas closer to the galactic center orbits faster than gas farther out. As the bubble expanded over millions of years, different parts of it were sheared by this rotation. This shear can stretch the bubble along the direction of rotation, twist its boundaries, and misalign different sections. What might have started as a more compact cavity becomes elongated and skewed as the galaxy itself moves beneath it. The vertical dimension is especially telling. The local bubble extends farther above and below the galactic plane than it does within the plane. This gives it a chimney-like structure rather than a round one. The reason is straightforward. Gas density drops rapidly away from the plane, so expansion encounters less resistance in those directions. These vertical extensions are not symmetric either. One side may open more than the other, depending on local conditions and the timing of energy input. Some maps show clearer openings toward one galactic pole than the other. Another source of irregularity is interaction with neighboring bubbles. The local bubble is not alone. Nearby cavities formed by other stellar groups expand at the same time. When two bubbles approach each other, their shells can merge, distort, or break apart. In some directions, what looks like the edge of the local bubble may actually be a shared boundary with another cavity. In others, the bubble may have ruptured, allowing hot gas to leak into a larger structure. These interactions erase clean outlines and create complex, interconnected shapes. Dense clouds embedded in or near the bubble also affect its form. When an expanding front hits a dense molecular cloud, it slows dramatically. The bubble may wrap around the cloud, leaving a dent or indentation in its boundary. Over time, this produces highly non-spherical contours. Some of these clouds can survive inside the bubble for long periods, acting as internal obstacles that shape internal flows. Their presence contributes to the irregular internal structure seen in detailed maps. The bubble's boundary itself is not smooth. It is wrinkled, fragmented, and clumpy. Instead of a single continuous shell, the edge is made up of filaments and arcs of denser gas. These structures trace where material was swept up and compressed, but they do not form a perfect enclosure. Because of this, defining the bubble's shape depends on what you choose to trace. If you map hot gas, the bubble may look larger and smoother. If you map neutral gas or dust, it may appear smaller and more fragmented. Different tracers highlight different aspects of the same underlying structure. From our vantage point inside the bubble, perspective also matters. We are seeing the structure from within, not from outside. Lines of sight pass through long, oblique paths that can exaggerate some features and hide others. What looks like a sharp boundary in one direction may be a gradual transition in another. Modern three-dimensional reconstructions make this clear. When the local bubble is visualized as a volume rather than a projected shape on the sky, it looks more like a misshapen cavity carved into a block of uneven material than a balloon. This weird shape is not a failure of models. It is exactly what physics predicts for a structure formed by multiple energy sources expanding into a turbulent, magnetized, rotating medium. Smooth spheres are the exception, not the rule. The irregularity also tells astronomers something useful. Each distortion, extension, or flattened region encodes information about past conditions. Where expansion was easiest, where it stalled, where it broke through, all of these features point back to the density, magnetic fields, and energy input at the time of formation. In that sense, the local bubble's shape is a fossil record. It preserves clues about where supernovae occurred, how the surrounding gas was arranged, and how the galaxy influenced expansion over time. The fact that it is not a perfect sphere is not just a detail. It is central to understanding what the local bubble is and how it formed. A smooth, symmetric cavity would imply a simple origin. The distorted shape we actually see implies a complex, dynamic history. Living inside this structure means we are surrounded by an environment that is uneven in every direction. The space above us is not the same as the space below. The space toward one constellation is not the same as toward another. All of it reflects the strange, lopsided geometry of a bubble shaped by violence, resistance, and motion over millions of years. The inside of the local bubble is not empty space. It is a distinct physical environment with properties very different from the surrounding interstellar medium. Density, temperature, composition, and motion inside the bubble all reflect the energetic events that created it. The most defining feature of the bubble's interior is how thin it is. Gas density inside the local bubble is extremely low, typically around a few thousandths of an atom per cubic centimeter. In some regions, it may be even lower. For comparison, average interstellar space outside the bubble often has densities hundreds of times higher, and dense clouds can be millions of times denser. Despite this extreme thinness, the gas inside the bubble is hot. Temperatures are commonly estimated to be between 1 and several million Kelvin. This combination, high temperature and low density, is a hallmark of gas heated by supernova explosions. The energy from those explosions was sufficient to raise particle energies dramatically, but the expansion diluted the gas before it could cool. This hot gas exists primarily as plasma. At these temperatures, atoms are ionized, meaning electrons are stripped from nuclei. The interior of the bubble is therefore dominated by charged particles rather than neutral atoms. This has important consequences for how the gas behaves, especially in the presence of magnetic fields. Because the density is so low, collisions between particles are rare. Heat does not flow the way it does in everyday materials. Instead of smooth conductive transfer, energy is carried by particles, moving long distances before interacting. This makes the interior environment more turbulent and less uniform than the temperature numbers alone might suggest. One of the main ways astronomers know this hot gas exists is through X-ray emission. At million-degree temperatures, ionized gas emits soft X-rays as electrons interact with ions. The diffuse X-ray glow observed across much of the sky is one of the strongest indicators that we are surrounded by hot plasma. However, the bubble's interior is not uniformly hot. Temperature variations exist, shaped by the timing and location of energy input, as well as by cooling and mixing processes. Some regions may be hotter, others cooler, depending on how recently they were affected by supernovae. Embedded within this hot plasma are cooler structures. The local bubble contains small clouds of relatively denser, cooler gas drifting through its interior. These clouds are not remnants of the original dense material that formed the bubble's walls. Instead, they are thought to be fragments of interstellar material that either survived the bubble's formation or drifted in later. The most important of these for us is the local interstellar cloud, the region of gas the solar system is currently passing through. This cloud has a temperature of only a few thousand Kelvin, cool by interstellar standards, and a density much higher than the surrounding bubble interior, though still extremely low compared to Earth's atmosphere. These embedded clouds are partially ionized and threaded by magnetic fields. Their edges interact with the hot plasma, leading to evaporation, compression, and complex boundary layers. Over long timescales, these clouds may shrink, fragment, or be absorbed into the surrounding hot gas. Dust is scarce inside the bubble. Much of the original dust was destroyed by shock waves or swept to the bubble's edges during expansion. As a result, the interior has relatively low dust content compared to surrounding regions. This is why nearby space appears unusually clear in many directions, with minimal reddening of starlight. The lack of dust affects chemistry. Many molecules form on dust-grained surfaces, so molecular gas is rare inside the bubble. The interior is dominated by atomic and ionized gas, rather than complex molecules. Star formation does not occur inside the hot interior itself. It is confined to cooler, denser regions at the edges or in embedded clouds. Magnetic fields permeate the bubble's interior, though their strength and orientation differ from those outside. As the bubble expanded, magnetic field lines were stretched and rearranged. Inside the cavity, fields tend to be weaker and more disordered, while stronger, more compressed fields accumulate at the boundaries. These magnetic fields influence how charged particles move. They guide the flow of plasma, affect turbulence, and play a role in how cosmic rays propagate through the region. The interior of the bubble is therefore not a simple, static plasma, but a magnetized, dynamic environment. Turbulence is another key feature. The energy injected by supernovae did not simply go into smooth expansion. A significant fraction was converted into turbulent motion. Even millions of years later, this turbulence can persist, slowly decaying as energy cascades to smaller scales. This turbulent motion stirs the hot gas, mixes material from different sources, and creates fluctuations in density and temperature. These fluctuations complicate observations, making it difficult to assign single values to the bubble's properties. Chemical composition inside the bubble reflects its violent origin. Supernovae enrich the interior with heavy elements, including oxygen, neon, and iron. These elements are present in ionized form and contribute to the observed X-ray emission. Over time, this enriched material will mix back into the broader interstellar medium. The pressure inside the bubble is dominated by thermal energy, but it also includes contributions from magnetic fields, turbulence, and cosmic rays. This combined pressure helps support the cavity against collapse. Even though the gas density is low, the high temperature means the pressure is not negligible. Radiation fields inside the bubble differ from those outside as well. With less dust to absorb ultraviolet light, radiation from nearby stars can travel farther. This affects ionization levels and the heating of embedded clouds. Despite its extreme conditions, the interior of the local bubble is not directly hostile to planetary systems. The distances involved are vast, and the densities are too low for the hot gas to have noticeable effects on planets or atmospheres. Its influence is subtle, operating through boundary conditions rather than direct interaction. One of the clearest impacts is on the heliosphere. The pressure, density, and magnetic field of the surrounding medium determine how far the solar wind can push outward. The fact that we are embedded in a hot, low-density environment allows the heliosphere to extend farther than it would in denser interstellar space. Over time, as the bubble cools and evolves, its interior conditions will change. But on human timescales, the environment inside the local bubble is effectively stable. The hot plasma, embedded clouds, and magnetic fields form a background that changes slowly over millions of years. Understanding what's inside the bubble is essential for interpreting observations of nearby space. Every measurement of starlight, cosmic rays, or interstellar gas near the Sun is influenced by this environment. The local bubble is not just something we sit in. It is the medium through which we observe the rest of the galaxy. The local bubble does not fade gently into the rest of the galaxy. Its interior environment ends where surrounding interstellar space begins to reassert itself. That transition happens at the bubble's edges, and those edges are some of the most structured and important regions in the local Milky Way. Outside the bubble, the interstellar medium looks much more typical. Gas densities rise sharply. Temperatures drop from millions of degrees to thousands or even tens of degrees, depending on the phase of the gas. Dust becomes abundant again. Molecules reappear. The environment shifts from a hot, ionized plasma to a mix of atomic, molecular, and dusty material. This change is not instantaneous. The bubble's boundary is not a thin wall, but a region of transition that can span tens of light years. Within this zone, conditions vary rapidly with position. Hot gas from inside mixes with cooler gas from outside. Magnetic fields become compressed and ordered. Density fluctuates on many scales. The most prominent feature of this boundary region is the accumulation of swept-up material. As the bubble expanded, it pushed surrounding gas and dust outward. That material did not vanish. It piled up at the edges, forming shells, arcs, and filaments of denser interstellar matter. These shells are visible in multiple ways. Dust maps show increased reddening. Radio observations reveal enhanced emission from neutral hydrogen. Molecular tracers light up in some regions, indicating the presence of cold, dense gas. Together, these observations outline the irregular walls of the local bubble. Many well-known nearby molecular clouds sit right along these boundaries. Their positions are not accidental. The compression caused by the expanding bubble helped shape them. In some cases, that compression may have triggered their formation or influenced their internal structure. At the edges, pressure balance becomes critical. Inside the bubble, pressure is dominated by hot gas. Outside, pressure comes from cooler gas, magnetic fields, and turbulence. Where these pressures meet, complex dynamics arise. Gas can flow along the boundary, fragment, or collapse locally. Magnetic fields are particularly strong at the edges. As the bubble expanded, it swept up and compressed magnetic field lines along with gas. This compression increases magnetic pressure and affects how matter moves. It can stabilize some regions against collapse while encouraging fragmentation in others. The result is a boundary that is anything but smooth. Instead of a uniform shell, the edge of the local bubble is broken into filaments and knots. Some regions are thick and dense, others are thin or porous. In places, the bubble appears to leak, allowing hot gas to escape into neighboring cavities. These leaks are not random. They tend to occur where the surrounding medium was already thin or where multiple bubbles intersected. In such regions, the local bubble's edge may open into a larger network of low-density space rather than closing off cleanly. Outside the bubble, the interstellar medium resumes its layered structure. Cold molecular clouds coexist with warmer atomic gas and ionized regions around hot stars. Star formation becomes possible again, especially in dense molecular clouds that were compressed during the bubble's expansion. This connection between bubble edges and star formation is one of the most important consequences of bubble formation. The same process that evacuates the interior creates conditions favorable for new stars at the boundary. Over time, generations of stars can form in a rough ring around an old bubble. Some of these newly formed stars may later produce their own winds and supernova, carving new bubbles that overlap with the old one. In this way, bubble edges become sites of ongoing activity rather than static remnants. The local bubble's edges also mark a transition in chemical composition. Inside, gas is enriched by supernova ejecta and dominated by ionized material. Outside, the chemical makeup reflects a mix of older interstellar material and locally processed gas. At the boundary, these materials mix, redistributing heavy elements. Radiation conditions change sharply across the boundary as well. Inside the bubble, ultraviolet radiation can travel farther due to low dust content. Outside, dust absorbs and scatters radiation, creating more shielded environments. This affects ionization, heating, and chemistry in the gas. From an observational standpoint, the edges are easier to detect than the interior. Dense gas and dust produce stronger signals across many wavelengths. This is why many maps of the local bubble focus on outlining its boundaries rather than detailing its interior. The sun's proximity to these edges varies by direction. In some parts of the sky, dense gas lies relatively close, just a few hundred light-years away. In others, the boundary is farther out or blends into other cavities. This uneven proximity affects how we observe distant objects. For example, when looking toward dense boundary regions, starlight is more strongly absorbed and reddened. In directions where the bubble opens into other cavities, the line of sight may remain relatively clear for much greater distances. Cosmic rays also behave differently near the edges. Changes in magnetic field strength and orientation can reflect, trap, or redirect charged particles. The boundary region acts as a complex filter, influencing which particles can reach the interior and which are deflected. Over millions of years, the edges of the local bubble evolve. As internal pressure decreases, expansion slows. Surrounding gas may begin to flow back in. Shells can fragment or collapse. New stars can form. The sharp contrast between inside and outside gradually softens. But even as it evolves, the boundary remains a record of past activity. Its structure reflects where energy was injected, how gas was distributed, and how magnetic fields responded. Reading that structure allows astronomers to reconstruct the history of the bubble. What lies outside the local bubble is not empty space waiting to fill a hole. It is an active, structured interstellar environment that has been shaped, compressed, and reorganized by the bubble's growth. The edges are where the bubble's influence is most visible and where its interaction with the rest of the galaxy is most intense. From our position inside, those edges define the limits of our immediate galactic neighborhood. Beyond them, space returns to a more typical state, denser, dustier, and more conducive to star formation. The contrast between inside and outside is what makes the local bubble such a distinctive feature of the Milky Way. The local bubble is not just a leftover cavity from ancient explosions. It shows evidence of ongoing motion. Parts of its structure are still expanding, and understanding why requires looking at pressure, energy balance, and the timescales involved in how hot gas behaves in the interstellar medium. At the most basic level, expansion happens because the interior of the bubble has higher pressure than its surroundings. Pressure in a gas depends on both temperature and density. Inside the local bubble, density is extremely low, but temperature is very high. Outside the bubble, density is higher, but temperature is much lower. When these factors are combined, the pressure inside the bubble remains comparable to or higher than that of the surrounding medium. This pressure difference drives expansion. Hot gas pushes outward against cooler, denser gas. As long as the internal pressure exceeds the external pressure, the bubble will continue to grow or at least resist collapse. The source of that pressure is energy injected by supernova and stellar winds. Although the supernovae that formed the local bubble occurred millions of years ago, the energy they deposited has not vanished. Because the gas density inside the bubble is so low, cooling is inefficient. The hot plasma loses energy slowly, allowing elevated pressure to persist for long periods. Cooling in interstellar gas happens mainly through radiation. At high densities, particles collide frequently, emitting radiation efficiently and cooling quickly. Inside the local bubble, collisions are rare. Even though individual particles are energetic, they don't interact often enough to shed that energy rapidly. As a result, the gas stays hot for tens of millions of years. This slow cooling means the bubble can remain overpressured long after the last supernova exploded. Expansion does not require a continuous energy source in the present. It only requires that the internal energy has not yet dissipated. Another factor is momentum. When the bubble expanded rapidly during its early stages, it imparted outward momentum to the surrounding shell of gas. Even as pressure differences decrease, that shell can continue moving outward due to inertia. Over time, interaction with surrounding material slows it down, but the motion does not stop instantly. The local bubble's expansion is therefore not uniform. Some regions may still be moving outward noticeably, while others have slowed or stalled. Expansion speed depends on local conditions, surrounding gas density, magnetic field strength, and whether the bubble encounters obstacles like dense clouds. In directions where the bubble meets dense material, expansion slows more quickly. Pressure equalizes sooner, and the boundary becomes more stable. In directions where surrounding density is lower, expansion can persist longer, allowing the bubble to stretch and connect with neighboring cavities. Vertical expansion plays a special role. Away from the galactic plane, gas density drops sharply. This makes it easier for hot gas to continue expanding upward and downward. Even if expansion within the plane has slowed, vertical flow can persist, venting hot gas toward the halo. This venting reduces internal pressure gradually but also reshapes the bubble, creating elongated structures and openings. The bubble does not simply inflate like a balloon, it evolves into a complex shape as gas finds paths of least resistance. Magnetic fields influence expansion in subtle ways. They add an additional form of pressure and tension that resists compression. In some directions, strong magnetic fields can slow expansion. In others, field lines may guide hot gas outward more efficiently. This anisotropic behavior contributes to uneven expansion. There is also evidence that not all energy input occurred at the same time. Some supernovae likely exploded later than others, possibly even after the initial cavity had formed. These later events would have reheated parts of the bubble, locally increasing pressure and renewing expansion in specific regions. The local bubble may therefore be in a mixed state, some sections coasting from ancient momentum, others driven by residual pressure, and still others influenced by more recent energy injections. interactions with neighboring bubbles can also drive apparent expansion. When two cavities approach each other, their boundaries may shift, merge, or rearrange. What looks like expansion in one direction could partly reflect the combined evolution of multiple structures. It's important to note that expansion does not mean rapid growth. Current expansion speeds, where measurable, are modest by astronomical standards, on the order of a few kilometers per second or less. At these speeds, noticeable changes occur over millions of years, not human lifetimes. Eventually, expansion will slow to a halt. As the interior gas cools further and pressure equalizes with the surroundings, the driving force disappears. At that point, the bubble may begin to fragment, collapse partially, or dissolve into the surrounding interstellar medium. But the local bubble has not yet reached that stage. Its interior remains hot. Pressure remains elevated. Boundaries in some regions still show signs of outward motion. In that sense, it is a structure that is still evolving, not a fossil frozen in time. The fact that the bubble is expanding at all tells astronomers something important about its age. If it were very old, cooling and pressure loss would have erased any expansion signatures. The persistence of expansion implies that the bubble formed relatively recently, on galactic timescales, within the last few tens of millions of years. Expansion also helps explain the bubble's shape. Regions that expanded longer or faster appear larger. Regions that encountered resistance appear smaller or compressed. The present-day geometry is a direct outcome of where and how expansion continued. From inside the bubble, this expansion is not something we feel or notice directly. The changes are far too slow. But by measuring gas motions, shell velocities, and pressure gradients, astronomers can detect these subtle dynamics and piece together the bubble's current state. The local bubble is therefore not just an empty cavity left behind by past explosions. It is a dynamic structure still responding to the energy that created it. Its expansion is the lingering echo of stellar deaths, playing out over millions of years in the space around us. Detecting the expansion of the local bubble is not straightforward. We are inside the structure, the motions are slow, and the distances are vast. There is no obvious expanding shell racing across the sky. Instead, astronomers have to rely on indirect measurements, subtle velocity signatures, and statistical patterns spread across many observations. One of the primary tools is spectroscopy. Gas moving toward or away from us leaves a clear signature in the light it absorbs or emits. Because of the Doppler effect, motion along the line of sight shifts spectral lines to slightly different wavelengths. By measuring these shifts, astronomers can determine the speed of gas relative to the Sun. In the case of the local bubble, absorption lines from interstellar gas seen in the spectra of nearby stars are especially valuable. When gas at the bubble's edge moves outward, its motion can produce systematic velocity patterns. Gas on the near side of an expanding shell tends to move toward us, while gas on the far side moves away. These velocity signatures are small, often just a few kilometers per second, but they are measurable with high-resolution instruments. By compiling data from many stars in different directions, astronomers can look for coherent patterns consistent with expansion rather than random motion. Neutral hydrogen observations in the radio band provide another important method. The 21-centimeter emission line of hydrogen allows astronomers to map both the distribution and velocity of neutral gas. At the boundaries of the local bubble, neutral hydrogen shows velocity structures that differ from the surrounding medium. In some regions, these velocities are consistent with gas being pushed outward. In others, they show signs of shear or interaction with neighboring structures. While not all boundary gas is expanding uniformly, these measurements help identify where expansion is still occurring. Ionized gas tracers offer complementary information. Certain ions observed in ultraviolet spectra are sensitive to specific temperature and ionization conditions. Their absorption lines can trace gas at the interface between the hot bubble interior and cooler surrounding material. These ions often show velocity components that differ from both the hot interior and the cold exterior, suggesting motion within the transition region. This is where expansion effects are most likely to be observed. X-ray observations contribute indirectly. While X-rays do not provide velocity information in the same way as optical or radio spectroscopy, they constrain temperature and pressure. By combining pressure estimates with density measurements, astronomers can infer whether the bubble interior should still be expanding. If internal pressure is significantly higher than external pressure, expansion is expected. If pressures are roughly balanced, expansion should be minimal. X-ray data therefore help determine whether observed motions are physically plausible. Distance measurements are critical for interpreting all of this. Without accurate distances to stars and gas clouds, velocity data are ambiguous. Modern astrometric surveys provide distances precise enough to place absorbing and emitting gas in three-dimensional context. This allows astronomers to separate local motions associated with the bubble from unrelated motions farther away. A velocity shift only indicates expansion if the gas is actually located at the bubble's boundary. Statistical modeling plays a major role. Individual measurements are noisy and affected by local turbulence, magnetic effects, and random motions. By analyzing large datasets and fitting models of expanding shells or cavities, astronomers can extract weak expansion signals from the background. These models test whether observed velocities align with what would be expected from expansion centered near the bubble's formation region. When multiple lines of evidence converge, confidence increases. Another approach involves studying pressure gradients directly. By comparing pressure inside the bubble to pressure outside, astronomers can assess whether the conditions favor expansion. Pressure estimates come from combining temperature, density, and magnetic field measurements. Magnetic field measurements themselves are obtained through techniques like Faraday rotation, which tracks how polarized radio waves twist as they pass through ionized, magnetized gas. Changes in magnetic field strength and orientation at the bubble's edge can indicate compression or stretching consistent with expansion. Timing constraints provide an additional check. The estimated age of the bubble, based on stellar motions and supernova histories, must be consistent with the observed expansion state. If the bubble were too old, expansion signatures would be unexpected. One of the challenges in measuring expansion is disentangling it from galactic rotation. The Milky Way's rotation produces large-scale velocity patterns that can mask or mimic expansion signals. Careful modeling is required to subtract these effects and isolate local motions. Another challenge is that expansion may not be symmetric. Some regions expand faster than others, while some may be stalled. Averaging over the entire structure can wash out localized expansion signals. This is why directional analyses are important. Importantly, no single observation proves expansion on its own. The case for expansion rests on the consistency of multiple methods pointing to the same conclusion, that parts of the local bubble's boundary are still moving outward at modest speeds. As instruments improve, especially in spectroscopy and distance measurement, these methods become more sensitive. Small velocity shifts that were once lost in noise can now be detected and placed in context. Measuring expansion is therefore less about watching the bubble grow and more about reading the subtle clues left in the motion and condition of interstellar gas. It requires patience, large datasets, and careful interpretation. The result is a picture of a structure that is not static. Even millions of years after its formation, the local bubble retains enough energy and momentum for its boundaries to continue evolving. The tools used to measure that evolution are indirect, but together they provide a coherent view of a bubble still responding to its origin. The local bubble is defined not just by what it lacks, but by how its remaining components behave. Gas, dust, and magnetic fields inside the bubble exist in a state shaped by extreme conditions and long-term evolution. Each component responds differently to the energy that created the bubble, and their interactions help maintain its structure. Gas inside the bubble is overwhelmingly hot and ionized. Most atoms have lost one or more electrons, turning the gas into plasma. Because densities are so low, this plasma behaves differently than gas in denser regions. Collisions are rare and particles travel long distances before interacting. This allows energy and momentum to spread over large volumes. The hot plasma is not uniform. Temperature and density vary from place to place, reflecting where supernova energy was deposited and how it dissipated. Some regions may still retain higher temperatures due to more recent heating, while others have cooled slightly over time. Ionized gas responds strongly to magnetic fields. Charged particles spiral along magnetic field lines, making the field a key factor in shaping gas motion. Instead of flowing freely in all directions, plasma tends to follow magnetic pathways, which contributes to anisotropic expansion and uneven internal structure. Neutral gas inside the bubble is rare but not absent. Small pockets of partially neutral gas exist, usually associated with embedded clouds. These regions are cooler and denser than the surrounding plasma, and they behave differently under magnetic and thermal forces. Dust is one of the most depleted components of the local bubble. During the bubble's formation, shockwaves from supernovae destroyed many dust grains through sputtering and collisions. Others were swept outward and concentrated at the bubble's edges. As a result, the interior contains far less dust than typical interstellar space. This has several consequences. Starlight travels through the bubble with minimal reddening. Ultraviolet radiation penetrates farther. Molecular formation is suppressed since many molecules rely on dust grain surfaces to form. The dust that does remain inside the bubble is often found within embedded clouds, where it is shielded from the hot plasma. Even there, dust grains may be altered with changed sizes or compositions due to past shock processing. Magnetic fields inside the bubble differ from those outside. During expansion, field lines were stretched, tangled, and partially evacuated along with gas. This led to a weaker and more disordered magnetic field in the interior compared to the compressed, ordered fields at the boundaries. Despite being weaker, the internal magnetic field still plays an important role. It contributes to total pressure, influences turbulence, and affects how cosmic rays move through the region. In a plasma, this hot and thin magnetic forces can be as important as thermal forces. At the bubble's edges, magnetic fields are stronger and more structured. As gas and dust piled up, so did magnetic field lines. This compression increases magnetic pressure and can help support dense shells against collapse. It also influences where gas can flow and where it becomes trapped. The interaction between gas and magnetic fields creates complex boundary layers. Hot plasma pushing against magnetized cooler gas can generate instabilities, mixing layers, and filamentary structures. These features are commonly seen in maps of the bubble's edges. Gas motions inside the bubble are turbulent. This turbulence is a leftover from the violent events that created the cavity. Over time, turbulent energy cascades to smaller scales and dissipates as heat, but the process is slow in low-density environments. Turbulence contributes to irregular density and temperature patterns. It can stir enriched material from supernova ejecta throughout the bubble, helping to homogenize chemical composition over long timescales. Chemical enrichment inside the bubble reflects its origin. Supernovae injected heavy elements into the interior, and those elements remain mixed into the hot plasma. Over time, this enriched gas may cool and rejoin the broader interstellar medium, contributing to the galaxy's chemical evolution. Gas, dust, and magnetic fields also interact with radiation inside the bubble. With less dust to absorb light, radiation fields are stronger and more uniform. This affects ionization states and heating rates, especially near embedded clouds. The combined pressure from hot gas, magnetic fields, turbulence, and cosmic rays maintains the bubble's structure. No single component dominates everywhere. Instead, the balance varies by location, producing a complex, multi-pressure environment. This balance is dynamic. As gas cools, magnetic fields relax, and turbulence decays, the relative importance of each component shifts. These changes occur slowly, but they shape how the bubble evolves over millions of years. Understanding these components is essential for interpreting observations. Absorption lines depend on gas density and ionization. Dust maps depend on grain distribution. Polarization measurements trace magnetic fields. Each probe reveals a different slice of the bubble's internal physics. The local bubble is therefore not just a hollow space left behind by explosions. It is a magnetized, turbulent plasma environment with altered chemistry and depleted dust. Its internal conditions are the result of long-term interaction between gas, dust, magnetic fields, and energy injected by stars. From our position inside it, these components form the background medium through which the solar system moves. They quietly shape how space behaves around us, even though their effects are subtle and unfold on timescales far beyond human experience. The local bubble is not just a structure of gas and magnetic fields. It is also an environment shaped by high-energy particles and radiation. Cosmic rays, ultraviolet light, and X-rays behave differently inside the bubble than they do in denser regions of the galaxy. And those differences reveal important details about the bubble's history and current state. Cosmic rays are fast-moving charged particles, mostly protons, with a smaller fraction of heavier nuclei and electrons. They are produced by energetic processes such as supernova explosions and the shocks associated with them. Because the local bubble was created by multiple supernova, it is tightly linked to the origin and propagation of cosmic rays in our region of the Milky Way. Inside the bubble, cosmic ray densities and energies are shaped by two main factors: the initial injection of particles and how they move through the bubble's magnetic field. Supernovae not only heated the gas but also accelerated particles to near-relativistic speeds. Many of those particles remained in the region rather than escaping immediately into the broader galaxy. The low density of the bubble's interior affects how cosmic rays lose energy. In denser gas, cosmic rays collide more often with atoms, gradually losing energy and producing secondary particles and radiation. Inside the local bubble, collisions are rarer, allowing cosmic rays to travel longer distances without significant energy loss. Magnetic fields play a crucial role in guiding cosmic rays. Because these particles are charged, they spiral along magnetic field lines rather than moving in straight paths. Inside the bubble, where magnetic fields are weaker and more disordered, cosmic ray paths are more tangled and less confined than in denser, more strongly magnetized regions. This means cosmic rays can spread more easily throughout the bubble's interior. Rather than being trapped in small regions, they fill the cavity relatively uniformly. However, their motion is still not free. Even weak magnetic fields are enough to significantly influence charged particle trajectories. At the bubble's edges, the situation changes. Stronger, compressed magnetic fields can partially reflect or trap cosmic rays. This creates a boundary effect where some particles are contained within the bubble longer than they would be in a uniform medium. Others may be redirected along the boundary rather than escaping directly. These effects influence the cosmic ray flux that reaches the solar system. The local bubble acts as a filter, modifying the energy spectrum and directionality of cosmic rays arriving at Earth. While the overall cosmic ray background is dominated by distant sources, local structures like the bubble leave subtle imprints. Radiation inside the bubble also differs from surrounding space. One of the most prominent features is diffuse X-ray emission. Hot, ionized gas at million-degree temperatures emits soft X-rays, which have been observed across much of the sky. This emission is a key indicator of the bubble's hot interior. X-rays from the bubble are not uniform. Their intensity varies with direction, reflecting changes in gas density, temperature, and line-of-sight distance through the hot plasma. In directions where the bubble is larger or more open, X-ray emission is stronger. Ultraviolet radiation also plays an important role. With little dust to absorb or scatter it, ultraviolet light from nearby stars travels farther inside the bubble than it would in denser regions. This leads to higher ionization levels in embedded clouds and boundary regions. The combination of cosmic rays and ultraviolet radiation affects the chemistry of the gas. Ionization influences how atoms and molecules form, break apart, and interact. Inside the bubble, chemical pathways differ from those in dust-rich molecular clouds, favoring simpler atomic and ionic species. Cosmic rays contribute to ionization as well. Even in regions shielded from ultraviolet light, cosmic rays can penetrate and ionize gas. Inside the bubble, where cosmic rays can propagate efficiently, this ionization source remains important, especially within embedded clouds. Radiation pressure is not a dominant force inside the bubble, but radiation still shapes energy balance. Ultraviolet and X-ray photons heat gas, maintain ionization, and influence how quickly different regions cool. The bubble's radiation environment also preserves a record of its past. Elevated cosmic ray levels and hot gas emission point to recent energetic activity on galactic timescales. If the bubble were much older, these signatures would have faded as particles escaped and gas cooled. From an observational perspective, separating bubble-related radiation from other sources is challenging. Emission from the heliosphere, distant galactic gas, and extragalactic backgrounds all overlap. Careful modeling is required to isolate what truly comes from the local bubble. Despite these challenges, the presence of diffuse X-ray emission and modified cosmic ray behavior remains one of the strongest pieces of evidence that we are inside a hot, low-density cavity. For Earth, the effects are subtle but real. The local bubble influences the baseline cosmic ray environment the planet experiences over long timescales. It shapes the radiation background in which the solar system moves, even though short-term variations are dominated by solar activity. On geological timescales, changes in the surrounding interstellar environment, including transitions into or out of regions like the local bubble, may influence cosmic ray exposure at Earth. These effects are still an area of active research. Inside the bubble, cosmic rays and radiation are not just byproducts. They are active components of the environment, interacting with gas and magnetic fields and carrying information about the bubble's origin and evolution. The local bubble is therefore a high-energy environment in a quiet form. Its radiation is diffuse, its particles invisible to the eye, but together they define the energetic backdrop of our local galactic neighborhood. The Sun is not stationary within the local bubble. Like every star in the Milky Way, it follows an orbit around the galactic center and moves relative to the surrounding interstellar medium. That motion means the solar system is traveling through the bubble, crossing different regions with different physical conditions. The Sun's speed relative to nearby interstellar gas is on the order of tens of kilometers per second. At these speeds, it takes tens of thousands of years to traverse a single light year. Over millions of years, however, this motion becomes significant, allowing the Sun to move across large fractions of the bubble's interior. The local bubble itself is not static either. Gas within it flows, boundaries shift, and pressure gradients evolve. The Sun's journey is therefore relative not only to the galaxy but also to a changing local environment. For much of its recent history, the Sun appears to have resided well inside the bubble, rather than near its edges. This conclusion comes from the low levels of dust and gas detected in many directions, and from the properties of nearby interstellar material. At present, the solar system is embedded within a small cloud of interstellar gas known as the local interstellar cloud. This cloud is a denser, cooler pocket drifting through the hot interior of the bubble. The Sun entered this cloud relatively recently on astronomical timescales, likely within the last few tens of thousands of years. Before entering the local interstellar cloud, the Sun would have been immersed directly in the bubble's hot plasma, with even lower surrounding gas density. That environment would have allowed the heliosphere to expand farther than it does today. As the Sun moves through the local interstellar cloud, it experiences a modest increase in surrounding density and pressure. Even so, this cloud is still extremely tenuous by everyday standards. The transition is subtle but measurable in terms of heliospheric structure and interstellar gas flow. The direction of the Sun's motion relative to the surrounding gas has been determined through measurements of interstellar atoms entering the solar system. Neutral atoms from the local interstellar medium flow through the heliosphere and can be detected by spacecraft, providing direct information about relative velocity and direction. These measurements show that the Sun is moving through the local gas rather than the gas flowing past a stationary Sun. This relative motion creates a kind of interstellar wind that interacts with the solar wind. Over longer timescales, the Sun's galactic orbit means it has not always been inside the local bubble. Tens of millions of years ago, before the bubble formed, the Sun would have been embedded in a more typical interstellar environment, likely denser and dustier than today. As the bubble expanded, it likely swept past the Sun rather than the Sun moving into it. In other words, the bubble formed around the solar system's general location. The Sun did not travel into an existing cavity. The cavity grew to encompass the Sun. This distinction matters because it places constraints on the timing of bubble formation. If the Sun has been inside the bubble for most of its existence, then the bubble must be relatively young on galactic timescales, consistent with estimates of its age. The Sun's motion also means that its position relative to the bubble's center and edges changes over time. Even within the bubble, conditions are not uniform. Temperature, density, and magnetic field strength vary from place to place. As the Sun drifts through these variations, the heliosphere responds. Its size, shape, and shielding effectiveness change slowly in response to external conditions. These changes are gradual and occur over tens of thousands to millions of years. On geological timescales, such variations may influence the cosmic ray flux reaching Earth. Denser or more magnetized regions can reduce cosmic ray penetration, while more tenuous regions may allow higher fluxes. These effects are subtle and remain an area of active study. The Sun's future path will eventually carry it closer to one of the bubble's boundaries, though this will take millions of years. At that point, the surrounding interstellar environment will change more dramatically, with higher densities and stronger magnetic fields. For now, the Sun remains comfortably inside the bubble's interior, moving through a region that is unusually clear and hot compared to the rest of the galaxy. This environment shapes the solar system's interaction with interstellar space in ways that are quiet but persistent. The journey of the Sun through the local bubble is a reminder that the solar system's environment is not fixed. Over long timescales, it changes as stars move and structures evolve. The local bubble is simply the current chapter in a much longer story of the Sun's passage through the Milky Way. The heliosphere is the region of space dominated by the solar wind, the continuous stream of charged particles flowing outward from the Sun. Its size, shape, and behavior are not determined by the Sun alone. They are strongly influenced by the properties of the surrounding interstellar medium. The local bubble sets the boundary conditions for the heliosphere in a way that is unusual compared to much of the galaxy. The basic structure of the heliosphere depends on a pressure balance. The outward pressure of the solar wind is opposed by the pressure of interstellar gas, magnetic fields, and cosmic rays outside the solar system. Where these pressures balance, the solar wind slows and eventually stops, forming the outer boundary of the heliosphere. Inside the local bubble, the interstellar gas density is exceptionally low. This means the external pressure acting on the heliosphere is lower than it would be in denser regions of the Milky Way. As a result, the solar wind can push farther outward before being stopped. This leads to a larger heliosphere than would exist in a typical interstellar environment. The Sun's protective bubble extends farther into space, creating a wider region where the solar wind dominates over interstellar influences. Temperature also matters. The hot plasma of the local bubble exerts pressure even at low density, but because it is highly ionized and diffuse, its interaction with the heliosphere differs from that of cooler, denser gas. The net effect still favors a relatively expanded heliosphere. The local interstellar cloud, which the Sun is currently passing through, slightly modifies this picture. This cloud has higher density than the bubble's hot interior, increasing external pressure somewhat. Even so, the environment remains far less dense than the average interstellar medium. As the Sun moves through regions of differing density within the bubble, the heliosphere responds by expanding or contracting slightly. These changes are slow, occurring over thousands of years, but they alter the heliosphere's size and shape. Magnetic fields are another critical factor. The interstellar magnetic field presses against the heliosphere and can distort it. Inside the local bubble, the magnetic field is weaker and more irregular than in denser regions, which reduces its ability to compress the heliosphere. However, even a weak magnetic field can shape the heliosphere's geometry. Observations suggest that the heliosphere is not spherical but asymmetric, with a nose pointing into the incoming interstellar flow and a trailing tail extending downstream. The direction and strength of the surrounding magnetic field influence this asymmetry. Because the local bubble's field is less ordered, the heliosphere may be less tightly confined and more variable in shape than it would be elsewhere. One of the most important roles of the heliosphere is shielding the solar system from galactic cosmic rays. The solar wind and its embedded magnetic field deflect and slow incoming charged particles, reducing the cosmic ray flux that reaches the inner solar system. The size of the heliosphere affects how effective this shielding is. A larger heliosphere provides a longer path through solar magnetic turbulence, increasing the likelihood that cosmic rays are deflected or lose energy before reaching Earth. By enabling a relatively large heliosphere, the local bubble indirectly reduces cosmic ray exposure in the inner solar system compared to what it might be in denser interstellar environments. This shielding is not constant. Solar activity cycles cause the heliosphere to expand and contract slightly, and long-term changes in the surrounding interstellar medium add another layer of variation. At the boundary of the heliosphere, interactions with the surrounding interstellar gas create complex structures. Neutral atoms from the interstellar medium can penetrate deep into the heliosphere before being ionized, while charged particles are mostly deflected. These interactions are influenced by the local bubble's conditions. Low external density means fewer interstellar neutrals enter the heliosphere, altering the balance of particle populations and energy exchange at the boundary. Spacecraft observations have provided direct evidence of these effects. Measurements of interstellar particles and fields show that the heliosphere's outer boundary responds to external pressure changes, confirming that it is sensitive to the surrounding environment. Over longer timescales, if the Sun were to leave the local bubble and enter a denser region of the galaxy, the heliosphere would shrink significantly. This would reduce its shielding effectiveness and alter the radiation environment throughout the solar system. Such transitions are not hypothetical. They have likely occurred in the past and will occur again in the future as the Sun continues its galactic orbit. For now, the local bubble provides a relatively gentle interstellar environment. It allows the heliosphere to remain large and effective, shaping the space weather conditions experienced by the planets. The influence of the bubble on the heliosphere is subtle and invisible to everyday experience, but it operates continuously. It defines how the solar system interfaces with the galaxy, setting the outermost boundary of the Sun's domain. In this sense, the local bubble is not just a distant astronomical structure. It directly affects the size and behavior of the region of space that protects Earth and the rest of the solar system from the wider galaxy. The local bubble feels unique because we live inside it, but it is not unusual in the Milky Way. Galactic bubbles are common features of star-forming galaxies, created wherever massive stars form, live briefly, and die violently. Comparing the local bubble to others helps place it in context and reveals what makes it typical and what makes it distinctive. Across the Milky Way, bubbles range widely in size. Some are only a few tens of light years across, carved by the winds of a single massive star. Others span hundreds or even thousands of light years, formed by multiple generations of stars acting together. The local bubble sits near the lower end of the large bubble category, larger than single-star wind bubbles, but smaller than the most extreme superstructures. Many galactic bubbles are associated with active star-forming regions. In these environments, clusters of massive stars inject energy continuously through winds and repeated supernova explosions. The resulting cavities are often hot, expanding, and surrounded by bright shells of gas and dust. The local bubble differs in that it is no longer powered by active massive stars. The stars that created it are gone. What remains is a cavity sustained by residual heat and momentum rather than ongoing energy input. In this sense, the local bubble is more evolved than many bubbles observed near star-forming regions. Age is a key point of comparison. Younger bubbles tend to have well-defined, rapidly expanding shells and strong shock signatures. Older bubbles like the local bubble show slower expansion, fragmented boundaries, and more complex internal structure. Cooling, mixing, and interaction with surrounding material have had time to reshape them. Shape is another difference. Many bubbles observed from outside appear roughly spherical or elliptical, at least initially. The local bubble, by contrast, is highly irregular. Its shape reflects not just its formation, but also its interaction with neighboring cavities and variations in the surrounding interstellar medium. This irregularity is not unique, but it becomes more apparent in older bubbles. As expansion slows and different regions evolve at different rates, symmetry breaks down. The local bubble's shape is therefore typical of a mature structure rather than an actively driven one. Environmental context matters. Some bubbles expand into relatively uniform surroundings, while others encounter dense clouds, spiral arms, or existing cavities. The local bubble formed in a complex region of the Milky Way, already shaped by prior generations of star formation. This contributed to its uneven growth and porous boundaries. Comparisons with superbubbles are especially informative. Superbubbles are enormous cavities created by dozens or hundreds of supernovae in large stellar associations. They can break out of the galactic disk and vent hot gas into the halo. The local bubble is smaller and less energetic than a classic superbubble, but it shares some characteristics. Like superbubbles, the local bubble shows evidence of multiple supernovae rather than a single event. It also shows signs of vertical expansion away from the galactic plane. However, it lacks the scale and energy needed to drive large-scale outflows into the halo. In contrast, smaller wind-blown bubbles formed by single stars are much simpler. They tend to be more spherical, with clearer boundaries and shorter lifetimes. The local bubble's complexity reflects its multi-source origin and long evolution. Another difference lies in observational perspective. Most bubbles are observed from outside, projected onto the sky as shells or arcs. The local bubble is observed from within, which makes its structure harder to visualize and requires different analysis techniques. This can make it seem more confusing or less defined than bubbles seen externally. When viewed statistically, the local bubble fits well within the range of properties expected for a bubble formed by a small group of massive stars over several million years. Its size, temperature, and pressure are consistent with theoretical models of such structures. What sets it apart is its proximity and the level of detail available. Because it is so close, astronomers can study it with higher resolution than most other bubbles. Small-scale features that would be invisible in distant bubbles become accessible here. This detailed view reveals complexity that likely exists in many bubbles but is rarely observed. The local bubble may therefore appear unusually intricate simply because we can study it so closely. Comparisons with bubbles in other galaxies reinforce this idea. Observations of nearby galaxies show networks of overlapping bubbles and cavities filling star-forming regions. These structures resemble scaled-up versions of what we see locally, suggesting similar processes at work. In those galaxies, bubbles often overlap and merge, creating large regions of hot, low-density gas. The local bubble appears to be part of such a network on a smaller scale, connected to neighboring cavities rather than isolated. From a galactic perspective, bubbles are a normal phase in the life cycle of interstellar gas. They redistribute energy, shape magnetic fields, and influence where stars form next. The local bubble is one example of this broader pattern. Comparing it to others helps remove the sense of uniqueness while highlighting its scientific value. It is not special because it exists, but because we can study it from the inside with exceptional detail. In that sense, the local bubble is both ordinary and extraordinary. Ordinary as a common product of stellar feedback, and extraordinary as a nearby laboratory for understanding how bubbles shape galaxies. Galactic bubbles do not just remove gas from regions of space, they rearrange it. In doing so, they play a direct role in where and how new stars form. The local bubble is a clear example of this process, showing how stellar feedback can both suppress and encourage star formation at the same time. Inside a bubble, star formation is effectively shut down. The gas is too hot and too diffuse to collapse under gravity. Even if small density fluctuations exist, thermal pressure overwhelms gravitational attraction. The interior becomes a star formation desert. This suppression is one side of the story. By heating and dispersing gas, bubbles prevent stars from forming in the regions they evacuate. In the local bubble, this has created a large volume of space near the Sun where no new stars are forming. The other side of the story happens at the edges. As the bubble expands, it sweeps up surrounding gas and dust into shells and filaments. This process increases density and pressure in those regions, sometimes by orders of magnitude compared to the original medium. When gas is compressed, it can cool more efficiently. Cooling reduces pressure support, allowing gravity to take over. Under the right conditions, this leads to the collapse of dense clumps and the formation of new stars. This mechanism is often called triggered star formation. The bubble itself does not create stars directly, but its expansion creates the conditions that make star formation more likely at specific locations. The local bubble's boundaries host many nearby molecular clouds. These clouds contain cold, dense gas and are active or potential sites of star formation. Their alignment with the bubble's edges suggests a causal link between bubble expansion and cloud formation. Compression is not the only influence. Magnetic fields swept up at the edges can guide gas flows, shaping filaments and controlling how material fragments. In some cases, magnetic pressure may delay collapse. In others, it may channel gas into dense ridges that later form stars. Timing matters as well. If compression is too rapid, turbulence may dominate and prevent collapse. If it is too slow, gas may disperse before stars can form. The local bubble's relatively moderate expansion speed appears compatible with cloud formation in several regions. Star formation triggered by bubbles is often clustered. Instead of isolated stars forming randomly, groups of stars form along shell-like structures. Over time, these clusters can create their own feedback, producing winds and supernovae that generate new bubbles. This creates a feedback loop. One generation of stars forms a bubble. That bubble triggers the next generation of stars at its edges. Those stars then form new bubbles, propagating star formation through the galaxy. The local bubble fits into this larger pattern. It likely formed from earlier star-forming activity, and its edges now host regions where new stars have formed or may form in the future. However, not all compressed gas becomes stars. Some shell material may remain stable or eventually disperse. Whether star formation occurs depends on local conditions, including gas mass, cooling efficiency, turbulence, and magnetic field strength. Observations of other bubbles show similar mixed outcomes. Some shells are rich in young stars, others are relatively sterile. The local bubble's edges show both behaviors in different directions. The effect of bubbles on star formation also depends on scale. Small bubbles may influence only a few clouds, while large superbubbles can reorganize entire regions of the galaxy. The local bubble's influence is intermediate, affecting a significant but not dominant volume. From a galactic perspective, bubbles contribute to the self-regulation of star formation. By heating and dispersing gas, they prevent runaway star formation. By compressing gas elsewhere, they ensure that star formation does not stop entirely. This balance helps explain why galaxies like the Milky Way form stars at a relatively steady rate over billions of years, rather than in short, intense bursts. In the local bubble, this balance has placed the Sun in a region with little nearby star formation, while surrounding areas remain active. This separation may be temporary on cosmic timescales, but it defines our current neighborhood. The presence of nearby young star clusters along the bubble's boundaries suggests that the local bubble has already influenced at least one generation of star formation. Over millions of years, as the bubble evolves and its boundaries shift, its role in shaping star formation will change. Compressed regions may collapse further or disperse. New bubbles may overlap and modify existing structures. The local bubble illustrates that star formation is not just about where gas exists, but how energy moves through that gas. Bubbles are one of the primary ways stars influence their environment and set the stage for the next generation. In this way, the local bubble is both a product of past star formation and an agent shaping future stars. It sits at the intersection of stellar death and stellar birth, quietly influencing where the Milky Way's next stars will appear. Galactic bubbles don't just clear space, they reorganize it. In doing so, they become one of the main ways stars regulate the birth of future stars. The local bubble shows this clearly. It suppresses star formation in some regions while encouraging it in others, all through the same physical process. Inside a bubble, star formation is effectively impossible. The gas is too hot and too diffuse. Gravity cannot overcome thermal pressure. Even if small density fluctuations appear, they are quickly erased by the surrounding heat. The interior becomes a long-lived region where stars simply do not form. This suppression matters. Without it, star formation could run away, rapidly converting large amounts of gas into stars. Bubbles act as a brake, removing gas from star-forming conditions and forcing it into a different phase. But the story does not end with suppression. As a bubble expands, it pushes outward on the surrounding interstellar medium. Gas and dust are swept up into shells, ridges, and filaments. In these regions, density rises and temperatures drop as the gas cools. This compression changes everything. When gas becomes dense enough, gravity can finally take over. Cooling accelerates. Turbulence begins to decay. Under the right conditions, fragments within the shell collapse and form stars. This process is known as triggered star formation. The bubble does not create stars directly. Instead, it creates the conditions that make star formation more likely in very specific places, mainly along its edges. The local bubble's boundaries host several nearby molecular clouds. These clouds are cold, dense, and structured, with properties consistent with having been shaped by external pressure. Their positions trace the irregular outline of the bubble rather than appearing randomly distributed. Compression alone is not sufficient. Magnetic fields, swept up with the gas, influence how that gas behaves. In some regions, magnetic pressure resists collapse, stabilizing the shell. In others, field lines channel material into narrow filaments, where collapse becomes easier. Timing also plays a critical role. If compression happens too violently, turbulence dominates and prevents collapse. If it happens too slowly, gas may disperse before stars can form. The local bubble's moderate expansion appears to fall into a regime where star formation is possible in select regions. Triggered star formation often produces clusters rather than isolated stars. Dense shells fragment into multiple collapsing regions at once. Over time, these clusters can produce massive stars of their own, which then inject energy back into the interstellar medium. This creates a chain reaction. One generation of stars forms a bubble. That bubble compresses gas and triggers the next generation. Those stars eventually create new bubbles, pushing star formation outward through the galaxy. The local bubble likely formed as part of this larger sequence. It was created by stars that formed earlier in the same region. Now its boundaries are influencing where future stars may appear. Not every compressed region forms stars. Some shells remain stable for millions of years, supported by magnetic fields or turbulence. Others fragment, but fail to collapse fully. The outcome depends on local conditions that vary along the bubble's edge. Observations of bubbles elsewhere in the Milky Way show the same pattern. Some edges are rich with young stars, others are quiet. The local bubble fits squarely within this broader behavior. On galactic scales, bubbles help regulate star formation by redistributing gas. They prevent stars from forming everywhere at once, while ensuring that star formation does not shut down completely. In the local bubble, this redistribution has placed the Sun in a region with little ongoing star formation. Nearby young stars tend to lie closer to the bubble's boundaries rather than near its center. Over millions of years, as the bubble evolves and its edges shift, this pattern will change. Compressed regions may collapse or disperse, and new bubbles may overlap with the old one. Star formation will move accordingly. The key point is that bubbles are not side effects of star formation. They are part of the process itself. They control where gas can collapse and where it cannot. The local bubble is a clear example of this feedback loop in action. It exists because stars once formed nearby, and it now shapes where the next stars may form. The local bubble is not a permanent feature of the Milky Way. It exists because energy was injected into the interstellar medium faster than that energy could dissipate. Over time, that imbalance fades. The future of the bubble is governed by cooling, pressure changes, and interaction with its surroundings. The most important long-term process is cooling of the hot interior gas. Even at very low densities, the plasma inside the bubble slowly loses energy through radiation. X-ray emission carries energy away, reducing temperature and pressure. This process is slow, but it is relentless. As the gas cools, internal pressure declines. When pressure inside the bubble drops below that of the surrounding interstellar medium, outward expansion stops. At that point, the bubble reaches a quasi-stable state where its boundaries no longer move significantly. Eventually, pressure may fall far enough that surrounding gas begins to flow back in. This infall does not happen uniformly. Dense regions move first, while lower density regions respond more slowly. The bubble does not collapse like a balloon popping. It erodes and fragments. Mixing plays a major role in this phase. Hot gas from the interior mixes with cooler gas from the edges, accelerating cooling and blurring the boundary. Chemical enrichment from supernova ejecta spreads outward, becoming part of the general interstellar medium. Magnetic fields also relax over time. Compressed field lines at the edges gradually untangle as pressure decreases. This changes how gas flows and can allow previously confined material to escape or redistribute. The embedded clouds inside the bubble face their own evolution. Surrounded by hot plasma, they slowly lose material through evaporation. Over millions of years, many will shrink or disappear entirely, adding their gas to the interior as it cools. Some clouds, however, may survive long enough to reach the bubble's edges, or form stars if conditions allow. Their fate depends on their mass, density, and magnetic shielding. Interactions with neighboring bubbles will continue to shape the local bubble's future. If nearby cavities expand or contract, boundaries may shift, merge, or dissolve. The local bubble may eventually lose its identity as a distinct structure, becoming part of a larger, more complex region. Vertical venting may persist for some time. As long as there are pathways of low resistance away from the galactic plane, hot gas can continue to flow outward, reducing internal pressure and hastening the bubble's decline. New energy injections are also possible. If a supernova occurs nearby within the bubble or at its edge, it could reheat portions of the interior or reshape the boundaries. The future evolution is therefore not strictly monotonic. On timescales of tens of millions of years, the most likely outcome is gradual dissolution. The local bubble will blend into the surrounding interstellar medium, leaving behind only subtle density and composition variations. For the solar system, this evolution will eventually matter. As the Sun moves through the galaxy, it may approach the bubble's edge or exit it entirely. The surrounding interstellar environment would then become denser and more magnetized. Such a transition would shrink the heliosphere and alter cosmic ray exposure throughout the solar system. These changes would occur slowly over thousands to millions of years, but they would mark a significant shift in the Sun's galactic environment. The local bubble's future is therefore tied to both internal processes and the Sun's motion. Even if the bubble persists for millions of years, the Sun may not remain inside it for its entire lifetime. What makes this future evolution scientifically valuable is that it follows well-understood physical processes. Cooling, mixing, and pressure balance operate the same way everywhere in the galaxy. By studying the local bubble, astronomers gain insight into how similar structures live and die elsewhere. The local bubble is currently in a middle-age phase. It is no longer rapidly expanding, but it has not yet faded away. Its future will be quieter than its past, marked by slow changes rather than dramatic events. Over time, the cavity carved by stellar explosions will soften, blur, and eventually vanish. The space around the Sun will become more typical of the Milky Way once again. For now, though, the local bubble remains a distinct feature of our galactic neighborhood, still evolving, still responding to the energy that created it, and slowly moving toward its eventual end. Despite decades of observation and modeling, galactic bubbles remain incomplete puzzles. The local bubble is one of the best studied examples, yet many of its fundamental properties are still uncertain. These open questions are not minor details. They shape how astronomers understand stellar feedback, interstellar structure, and the evolution of galaxies. One of the biggest uncertainties is the exact number and timing of the supernovae that created the local bubble. Evidence points to multiple explosions, but how many occurred, how energetic they were, and how closely spaced in time they were remains unclear. Different combinations can produce similar present-day structures. Closely related is the question of where those supernovae occurred. Small changes in their locations can significantly affect the bubble's shape and internal conditions. Reconstructing past stellar positions is difficult, especially over millions of years, and uncertainties compound quickly. The age of the local bubble is another open issue. Estimates generally place its formation within the last few tens of millions of years, but the range remains broad. Cooling rates, expansion signatures, and stellar motion constraints all provide partial answers, yet none are decisive on their own. The thermal structure of the bubble's interior is also debated. While million-degree gas is widely accepted, some observations suggest lower temperatures in parts of the interior. This raises questions about how uniformly the bubble was heated and how efficiently energy has been redistributed. The role of turbulence inside the bubble is poorly constrained. Turbulence affects mixing, cooling, and pressure balance, but it is difficult to measure directly. How long turbulence persists in such low-density environments remains an active area of research. Magnetic fields introduce further uncertainty. Their strength, geometry, and evolution inside the bubble are not fully mapped. Because magnetic fields influence gas motion and cosmic ray propagation, these uncertainties affect many other conclusions. Cosmic ray behavior inside the bubble raises additional questions. How long do cosmic rays remain trapped? How much do local structures alter the cosmic ray spectrum reaching Earth? These questions are challenging because cosmic rays are influenced by processes operating on many scales. The bubble's boundaries are also not fully understood. Are they continuous shells or are they highly porous? How much material leaks out? How much hot gas escapes into neighboring cavities or the galactic halo? The answers affect models of galactic gas circulation. The interaction between the local bubble and nearby bubbles is another open topic. It is unclear how distinct these structures truly are. What appears as a single bubble may be part of a larger, interconnected network. Observational limitations play a major role in these uncertainties. From inside the bubble, perspective complicates interpretation. Distance uncertainties, line-of-sight overlap, and background contamination all make it harder to isolate bubble-related features. Separating emissions from the bubble, the heliosphere, and distant galactic gas remains especially challenging in X-ray and ultraviolet observations. Improvements in instrumentation and modeling are gradually reducing this problem, but it is far from solved. Another unresolved issue is how typical the local bubble really is. While bubbles are common, the specific combination of size, age, and environment may not be. Determining whether our local conditions are representative affects how broadly conclusions can be applied. The influence of bubbles on long-term galactic evolution is also still being refined. How efficiently do bubbles transport energy and heavy elements? How much do they contribute to driving gas into the halo? The local bubble provides clues but not complete answers. Even the definition of a bubble is debated. Where exactly does the local bubble end? Is it a single structure or a collection of overlapping cavities? Different definitions lead to different interpretations. Future observations promise progress. Better distance measurements. higher resolution spectroscopy, improved polarization mapping, and more sensitive X-ray instruments will refine models of the bubble's structure and dynamics. Numerical simulations are advancing as well. More realistic models now include magnetic fields, cosmic rays, and multi-phase gas, allowing closer comparison with observations. Yet even with better tools, some uncertainty will remain. Galactic bubbles are inherently complex, shaped by chaotic processes and long timescales. The open questions surrounding the local bubble are not failures of understanding. They reflect the difficulty of studying dynamic, three-dimensional structures from a single vantage point inside them. What makes these questions compelling is that they connect small-scale physics to large-scale galactic behavior. By resolving them, astronomers move closer to understanding how stars shape the space between them and how structures like the local bubble fit into that story. The local bubble is easy to dismiss as a distant abstract structure, but it directly shapes the environment the solar system lives in. Its influence is not dramatic or immediate, but it is constant, setting the baseline conditions for everything that happens between the Sun and the rest of the galaxy. The most direct impact is on the space surrounding the solar system. The low-density, hot environment of the local bubble allows the heliosphere to remain large and extended. This changes how the solar wind interacts with interstellar space and how effectively it deflects incoming cosmic rays. Cosmic ray exposure at Earth is shaped by this environment. While solar activity dominates short-term variations, the local bubble defines the long-term background level. Over geological timescales, that background matters for atmospheric chemistry and radiation exposure. The clarity of nearby space is another consequence. With less dust in the bubble's interior, starlight reaches us with minimal absorption in many directions. This is one reason we can observe nearby stars and structures so clearly compared to denser regions of the galaxy. That clarity has shaped astronomy itself. Many of the stars and structures used to calibrate distances and test stellar models lie within or just beyond the bubble. Our understanding of the galaxy is influenced by the fact that our local region is unusually transparent. The local bubble also provides a record of nearby stellar explosions. The elements and radiation inside it are remnants of supernovae that occurred relatively close to the Sun in the recent past. Studying the bubble helps reconstruct that history. Those explosions were close enough in galactic terms to affect the local interstellar medium, but not close enough to harm life on Earth. The bubble is evidence of how common such events are and how the galaxy absorbs their energy without catastrophic consequences. On longer timescales, changes in the Sun's interstellar environment matter. As the Sun eventually approaches or exits the local bubble, the heliosphere will respond. Cosmic ray shielding will change. The radiation environment of the solar system will shift. These transitions are slow, but they are real. Understanding the local bubble helps predict what kinds of environments the solar system may encounter in the distant future. There is also a broader scientific reason this matters. The local bubble is one of the few galactic structures we can study from the inside with high resolution. It serves as a natural laboratory for testing models of stellar feedback, gas dynamics, and magnetic fields. What we learn here applies far beyond our neighborhood. The same processes shape star-forming regions, regulate galactic ecosystems, and influence how galaxies evolve over billions of years. The local bubble reminds us that the space around us is not passive. It is shaped by past events and still evolving. Even the region we call empty space has a history and a structure. From our perspective, the bubble is invisible. We do not see its walls in the night sky or feel its expansion. Yet it defines the context in which the solar system exists. Understanding the local bubble changes how we think about our place in the galaxy. We are not drifting through a uniform void. We are inside a structure created by stars that lived and died before the Sun finished forming. In that sense, the local bubble is part of our environment in the same way the atmosphere is part of Earth's. It is the medium that surrounds us, shapes what reaches us, and connects us to the larger galaxy. Knowing that matters because it turns our local patch of space from an abstract backdrop into an active, evolving system, one that continues to influence us, quietly and continuously. Subscribe.